113 WS. If you placed yourself at a truly random point in the observable universe, the most likely thing you would find in every direction is nothing. No galaxy, no star, no light, just the interior of a void stretching 100 million light years or more. Subscribe, there's a new one every few days. This is white space, settle in. On a clear night, far from the glow of any city, the sky appears to overflow. Every direction you turn, light. Thousands of points scattered across the dome of darkness, each one a sun, each one a fire burning across distances. The mind instinctively refuses to accept. The sky in that moment feels full, crowded almost, and that feeling, that intuitive sense of abundance is one of the most complete illusions the universe has ever produced. Part of what makes the illusion so convincing is the way time disguises itself as space. Every point of light you see in the night sky is a message from the past. The light from Sirius, the brightest star in the night sky, left its source 8.5 years ago. The light from Betelgeuse, the red supergiant that marks the shoulder of Orion, a star so large it would extend past the orbit of Jupiter if placed where our Sun is, left its source roughly 700 years ago. When you look at Betelgeuse, you are not seeing a star as it exists tonight. You are seeing a star as it existed in the 14th century during the height of the Black Death, when human civilization had no concept of what a star actually was. That light has been traveling since before the printing press, since before the Renaissance, since before the systematic practice of empirical science. And yet it arrives tonight, enters your eye, and your brain presents it as immediate, as present, as now. The Andromeda Galaxy, the smudge of light visible to the naked eye in autumn skies of the northern hemisphere, sent its photons toward us 2.5 million years ago, when our ancestors were making stone tools on the African savanna. Every direction you look into a different depth of time. The sky is not a snapshot, it is a palimpsest. This matters because it means that the night sky we observe is not a single consistent scene. It is a collage assembled from millions of different historical moments stitched together by the accident of when photons happened to arrive. We see nearby stars as they were 8 or 12 or 300 years ago. We see distant galaxies as they were hundreds of millions or billions of years ago. We see the cosmic microwave background as it was emitted 400,000 years after the Big Bang, from matter that now sits 46 billion light years away. All of this arrives simultaneously, and our senses evolve to navigate a world where distances are measured in meters and delays in fractions of a second, process it as a single unified present. The stars appear to be neighbors. They are not. They are isolated islands, separated by gulfs that dwarf the distances between continents, between planets and stars. And between those islands, there is almost nothing at all. Between the star Vega and the star Deneb, which appear close together in the summer sky of the northern hemisphere, lies approximately 230 light years of emptiness. Between our Sun and Tau Ceti, a star so similar to ours that astronomers have long considered it a candidate for hosting habitable worlds. There are nearly 12 light years of vacuum, roughly 113 trillion kilometers of nothing but stray photons, and the occasional atom of hydrogen. These are the spacings between individual stars within our local galactic neighborhood, and they already exceed comprehension. But the interstellar medium is not truly empty. It contains diffuse gas averaging about 1 atom per cubic centimeter, threaded by magnetic fields, populated by cosmic rays, and occasionally punctuated by molecular clouds, dense, cold reservoirs of hydrogen and organic molecules that represent the nurseries of future stellar systems. Even this tenuous material, invisible to the naked eye, is part of the structure of the galaxy, the substrate through which stars move, the medium from which they form, the reservoir into which they return when they die. Even the vast Oort cloud, the spherical reservoir of comets that extends from the outer solar system to roughly halfway between the Sun and the nearest stars, perhaps 50,000 astronomical units in radius, is, by the standards of interstellar space, vanishingly thin. A spacecraft traveling through the Oort cloud at its expected density of roughly 10 comets per cubic astronomical unit would almost certainly travel for years without coming within astronomical units of any object. Space is not merely big, it is overwhelmingly, almost insultingly empty. And we have not yet begun to discuss the spaces that make interstellar distances look like rounding errors. Between the Milky Way and the nearest large galaxy, the Andromeda Galaxy, lies 2.5 million light-years of intergalactic space. Between the Milky Way and the Virgo cluster, the nearest major galaxy cluster, the dense concentration of several thousand galaxies toward which we are slowly drifting, lies approximately 53 million light-years. Between the Virgo cluster and the Coma cluster, another major cluster visible in the northern sky lies roughly 300 million light-years. These are the distances between threads in the cosmic web. The threads themselves, the filaments along which galaxies accumulate, measure hundreds of millions of light-years in length. And the spaces enclosed within those threads, the regions between the filaments where almost nothing resides, are what we call voids. They are by volume the dominant feature of the universe. They are in a meaningful sense what the universe mostly is. They are called voids. In astronomical literature, the term refers to immense regions of space where galaxies are sparse to the point of near total absence. Not vacuums in the strict sense, even a void contains some diffuse gas, some stray particles, some faint tendrils of structure making their way toward the void's boundaries, but regions where the density of matter is anywhere from 15 to 50% below the cosmic average. The formal definition requires that the galaxy number density within the region fall below a specified threshold relative to the mean density of the universe, usually measured by counting galaxies within spheres of defined radius and comparing the count to the statistical expectation. Different surveys and different algorithms produce slightly different void catalogs. Because the boundaries of voids are not sharp, they blend into surrounding structure through a gradual transition zone where density rises from void interior to filament wall over a range of tens of megaparsecs. Their dimensions are staggering. A typical void spans between 30 and 500 megaparsecs across. To calibrate that number, 1 megaparsec equals roughly 3.26 million light-years. A void 100 megaparsecs in diameter contains a volume of space that dwarfs anything a human nervous system can meaningfully picture. A void 500 megaparsecs across is larger than the distance light has traveled since the universe was 3 billion years old. And the universe contains not one of these structures, but billions. Voids are not anomalies. They are the dominant feature of the cosmos at large scales. Most of the volume of the observable universe, by a substantial margin, is void. If you could place yourself at a random point in the observable universe, genuinely random, chosen without any bias toward the locations of galaxies or stars, there is an overwhelming probability that you would find yourself in a void surrounded by essentially nothing, with the nearest galaxy 100 million or more light-years away in every direction. Astronomers classify voids by size and depth. Mini-voids, sometimes called voids in the statistical sense, span only a few megaparsecs and are scattered throughout the cosmic web as the spaces enclosed within individual filament loops. Standard voids span tens of megaparsecs and are the most commonly studied. Supervoids span hundreds of megaparsecs and represent the largest coherent underdense regions in the observable universe. Nested within these categories is an important phenomenon: voids in voids. Large supervoids are not uniformly underdense throughout their interiors. They contain substructure, filamentary ridges, and sheets of slightly higher density that divide the supervoid's interior into smaller subvoids. These nested structures reflect the hierarchical nature of cosmic structure formation, the same gravitational instability that creates supervoids on large scales creates smaller voids within them, and smaller voids within those. The distribution of void sizes follows a statistical pattern that encodes information about the initial density fluctuations from which all structure grew, and about the dark energy that drives the accelerating expansion. The history of the universe can be read not only in the positions of galaxies today, but in the chemical composition of the matter within them. The abundances of the chemical elements, hydrogen, helium, lithium from the Big Bang, carbon, oxygen, nitrogen, silicon, iron, and everything heavier from stellar nucleosynthesis, carry a record of the physical processes that produce them. Big Bang nucleosynthesis, occurring in the first 3 minutes after the Big Bang, produced approximately 75% hydrogen and 25% helium by mass, with trace amounts of deuterium, helium-3, and lithium-7. The precise abundances are a sensitive probe of the conditions during those first minutes. Primarily the baryon to photon ratio, which determines how many baryons were present per unit of radiation, and the expansion rate at that epoch, which determines how long nucleosynthesis had to proceed before the universe cooled below the nuclear reaction threshold. Measuring the primordial helium abundance requires finding objects that have undergone as little additional nucleosynthesis as possible. Galaxies and gas clouds with the lowest possible heavy element content, so-called metal-poor environments where stellar processing is minimal. The most metal-poor galaxies known with heavy element abundances less than 2% of the solar value show helium mass fractions in their ionized gas regions of approximately 24 to 25%, consistent with the Big Bang prediction. The primordial deuterium abundance, measured in absorption spectra of distant quasars, where the quasar light passes through near-pristine intergalactic gas clouds at high redshift, provides a particularly clean probe of Big Bang nucleosynthesis because deuterium is destroyed rather than created in stellar interiors. Any deuterium observed in an ancient unprocessed gas cloud must be primordial. The measured deuterium abundance is approximately 2.5 parts per 100,000 by number relative to hydrogen, consistent with a baryon density that corresponds to the 5% of the critical density inferred from microwave background measurements. This agreement between completely independent methods, Big Bang nucleosynthesis and the microwave background, is one of the strongest consistency checks of the standard cosmological model. The interstellar medium within galaxies, the gas and dust between the stars, is chemically enriched by each generation of stellar evolution. Massive stars process hydrogen and helium into carbon, oxygen, neon, magnesium, silicon, and sulfur through successive nuclear burning stages, then explode in supernovae that produce iron, nickel, cobalt, and virtually all the elements heavier than iron through rapid neutron capture, the R process. The neutron-star mergers detected through gravitational waves are now confirmed as major sites of R process nucleosynthesis. Their neutron-rich ejecta seeding the surrounding interstellar medium with gold, platinum, europium, and the other heavy R process elements. Lower mass stars evolving more slowly produce carbon and nitrogen through hydrogen and helium burning in their interiors, then return this enriched material to the interstellar medium through stellar winds and planetary nebula ejection. The net effect, integrated over billions of years and billions of stars, is a gradual increase in the heavy element abundance of the interstellar medium. The process astronomers call chemical enrichment. Galaxies in voids are systematically less chemically enriched than galaxies of equivalent mass in filaments or clusters. Their stellar populations are younger on average, their star formation history is less completed, their heavy element abundance is lower. This reflects the quieter evolutionary history of void galaxies. Fewer mergers that trigger intense bursts of star formation, slower accretion of cold gas, longer timescales for the cumulative processes of nucleosynthesis. The void environment, in chemical terms, preserves a more primordial state galaxies that have had less time, fewer triggers, and fewer external inputs to drive the chemical evolution that their counterparts in denser environments have undergone. Studying the chemical properties of void galaxies provides a controlled laboratory for separating the intrinsic timescales of galaxy evolution from the environmental acceleration that operates in denser regions. The interstellar medium of our own galaxy, the medium through which the Sun is currently traveling, through which starlight passes and is partly absorbed, through which supernova shock waves propagate and molecular clouds condense, is a complex, multi-phase medium. Cold molecular gas, with temperatures as low as 10 Kelvin and densities of millions of molecules per cubic meter, forms the densest and coldest phase, the reservoirs from which stars form. Warm, neutral hydrogen gas at temperatures of about 10,000 Kelvin occupies a larger volume. Warm ionized gas at similar temperatures, but electrically ionized by ultraviolet radiation from nearby hot stars, fills a comparable fraction of the disk. Hot ionized gas at millions of Kelvin fills the local bubble and similar cavities carved by supernovae, occupying a substantial fraction of the disk volume despite its extreme rarefaction. These phases are not static. They exchange mass and energy continuously through the processes of stellar feedback. Radiation from hot stars ionizes their surroundings. Supernovae heat and compress neighboring gas. Stellar winds carve cavities, and the turbulence they drive mixes the phases together on scales from parsecs to kiloparsecs. The Sun's passage through different phases of the interstellar medium over its galactic orbit has implications for the solar system's environment and potentially for Earth's climate over geological timescales. When the solar system passes through a dense molecular cloud, an event that likely occurs roughly every few 100 million years, given the disk's structure, the heliosphere is compressed, potentially allowing more galactic cosmic rays to penetrate to the inner solar system. The increased cosmic ray flux may affect atmospheric ionization and cloud formation, modifying Earth's climate in ways that might be detectable in the geological record. Some researchers have searched for correlations between the timing of ice ages, mass extinctions, and other major events in Earth's geological history with the estimated timing of the solar system's passages through spiral arm structure and dense interstellar regions. The correlations are suggestive but contested, limited by the uncertainties in reconstructing the solar system's past trajectory through the galaxy and by the difficulty of establishing causal mechanisms. Cataloging voids systematically has become an industry in its own right. The VIDE Void Identification and Examination Toolkit applied to the Sloan Digital Sky Survey identified more than 1,000 distinct voids in the local universe alone. The Zuboff algorithm, zone bordering on voidness, uses the tessellation of galaxy positions into Voronoi cells, assigning each point in space to the nearest galaxy, then identifying underdes regions as zones where the Voronoi cells are large. Each method produces somewhat different catalogs because voids do not have sharply defined boundaries. They blend into surrounding structure through a gradual transition zone. But the statistical properties of voids, their size distribution, their depth, their shapes, are now measured well enough to serve as cosmological probes in their own right. The way voids cluster in space and the way their shapes are distorted by the peculiar velocity field surrounding them depends sensitively on the dark energy equation of state, the sum of neutrino masses and the growth rate of structure. DZ's void catalog will contain hundreds of thousands of objects, providing the most powerful void-based cosmological constraints ever assembled. Voids are not passive features of the cosmic landscape. They are dynamically active. Matter within a void experiences a net gravitational pull from the denser walls surrounding it. Not from within the void where there is little mass, but from the filaments and sheets at the void's periphery, which contain much more mass and therefore exert a stronger gravitational attraction. The result is that matter inside voids tends to flow outward, evacuating toward the surrounding structure. This flow is measurable in the peculiar velocities of galaxies near void boundaries. It is also self-reinforcing. As matter leaves the void becomes underdenser. The gravitational pull of the walls becomes relatively stronger, and the evacuation accelerates. Voids grow over time not merely because the universe is expanding, but because active gravitational dynamics continue to drain their interiors. In the language of cosmological perturbation theory, voids are the regions where the density contrasts delta. The fractional deviation from the mean density has become increasingly negative over time, reaching values as low as -1 in the most extreme cases, representing near total absence of matter. The existence of voids was not suspected by science for most of its history. The night sky, viewed without instruments, offers no hint of them. Even early telescopes revealed only more stars, more nebulae, more accumulated light. The true architecture of the universe at the largest scales began to emerge only in the 1970s, when a new generation of redshift surveys started to map not just where galaxies appeared on the sky, but how far away they were. Redshift, the stretching of light to longer, redder wavelengths as a source recedes, had been understood since Vesto Slipher's observations in the early 1910s. Slipher was the first to measure the recession velocities of what were then called spiral nebulae, finding speeds so large, hundreds of kilometers per second, that many astronomers initially dismissed his results. It was Edwin Hubble who in 1929 combined Slipher's recession velocities with his own distance measurements to nearby galaxies, using Sepchid variable stars, whose pulsation period is related to their intrinsic luminosity, and demonstrated the proportionality between distance and recession velocity that bears his name. The universe was expanding. This was not predicted by any existing theory. Einstein had introduced a cosmological constant into his equations specifically to prevent expansion, and famously called it his greatest blunder when Hubble's result was announced. But measuring redshifts for large numbers of galaxies simultaneously required patient spectroscopic work that only became practical with improvements in photographic and then electronic detector technology in the late 1970s. For the first time, astronomers could build three-dimensional maps of the galaxy distribution. And what those maps showed was not a uniform distribution. It was structure, enormous, unexpected, and deeply strange. Two independent research groups, working separately in 1978, identified for the first time the coexistence of massive galaxy superclusters and vast underdense regions between them. Gregory and Thomson, working with data from galaxies in the Perseus-Pisces region, found that the galaxies they surveyed were concentrated into a dense filamentary structure with comparatively empty space on either side. Simultaneously, Jan Einasto and colleagues in Estonia, working with a database compiled from the literature of previously measured galaxy redshifts, found the same general pattern in other regions of sky. Galaxies were not distributed uniformly, but in a web-like pattern of chains and clusters separated by regions of relative emptiness. These were the first recognized voids. The discovery was not immediately celebrated. Journals in the established astronomical literature were skeptical. Einasto has described submitting papers that described filaments and voids only to receive rejections from editors and referees who found the described structures implausible, too large, too empty, too inconsistent with the smooth, featureless universe that the prevailing cosmological models predicted. The standard model of the time? An Einstein-de Sitter universe, flat and matter-dominated, with structure growing slowly from small initial perturbations, simply did not naturally produce the kind of large, dramatic voids that observation was beginning to reveal. The universe, it seemed, did not match scientific intuition, but reality, as it tends to do, eventually made itself undeniable. The seminal technical conference that crystallized the modern understanding of large-scale structure took place in Tallinn, Estonia in 1977, just a year before the void discoveries were announced. Astronomers from across the world assembled at what was officially called the Joint Discussion on the Large-Scale Distribution of Galaxies at the International Astronomical Union Symposium. The discussions at that conference clarified the conceptual framework. The universe has a large-scale structure that can be studied statistically, that has physical meaning, and that any successful cosmological model must reproduce. The term large-scale structure, or in Russian, крупномасштабная структура Вселенной, entered the common vocabulary of the field at approximately this time and has remained central ever since. The confirmation that voids were not just statistical artifacts but genuine large-scale features of the cosmos came in 1981 when a team led by Robert Kirshner, Augustus O.M. Lair, Paul Schechter, and Stephen Schechtman conducted a targeted redshift survey in the direction of the constellation Boötes. Their survey was conducted in a narrow cone of sky, measuring the distances to all galaxies above a brightness threshold within that cone. When they plotted their results as a three-dimensional distribution position in the sky along two axes, distance along the third, they encountered a region of extraordinary emptiness. In a volume roughly 330 million light-years across, there were almost no galaxies where their statistical models predicted the presence of several dozen bright galaxies based on the number density observed in adjacent regions. They found exactly 3. The entirety of what became known as the Boötes void was essentially devoid of the luminous matter that marks the presence of ordinary galaxies. The Boötes void spans approximately 60 megaparsecs in diameter, roughly 200 million light-years, and sits approximately 700 million light-years from Earth. When the paper was published, the reaction within the astronomical community ranged from fascination to skepticism. Some astronomers wondered whether the survey had been miscalibrated, whether the brightness threshold had inadvertently excluded some faint galaxy population. Subsequent follow-up surveys confirmed the result. The void is real, it is large, and it is nearly empty. Later, deeper surveys identified a small number of galaxies within it. Perhaps 60 or more have now been catalogued, scattered across the void's interior at densities far below the cosmic average. These void galaxies are peculiar objects. They are predominantly late-type spirals with active star formation, bluer than the typical galaxy population. Their isolation means they have evolved in the absence of gravitational harassment from neighbors. They have not been stripped of their cold gas by ram pressure from intercluster medium, as happens to galaxies falling into dense clusters. They have not been distorted by tidal forces from nearby massive companions. They are, in a sense, the most undisturbed galaxies in the observable universe, relics of a simpler cosmic environment, evolving on their own timescale without the interruptions that shape galaxies in denser regions. The discovery of Boötes prompted a wave of deeper surveys. Astronomers began constructing wide-angle redshift catalogs, the CFA Redshift Survey, conducted by Margaret Geller, John Hutra, and colleagues at the Harvard-Smithsonian Center for Astrophysics through the 1980s and 1990s, the Las Campanas Redshift Survey in the early 1990s, which mapped 100,000 galaxies in 6 narrow slices of sky and produced some of the most striking visual representations of cosmic web structure ever generated. The 2-degree field galaxy redshift survey, which measured the redshifts of more than 200,000 galaxies in the southern sky, and ultimately the Sloan Digital Sky Survey, the most comprehensive redshift survey of the 20th and early 21st centuries, which measured the spectra and distances of more than 1 million galaxies across a large fraction of the northern sky. Each survey confirmed and refined the picture. The universe at large scales resembles a three-dimensional foam. Galaxy filaments and sheets form the walls of enormous bubbles. At the junctions where filaments intersect, the densest galaxy clusters accumulate, and inside the bubbles, stretching across hundreds of millions of light years, the voids reign. The picture also revealed something unexpected about the filaments themselves. Galaxy filaments, the threads of the cosmic web, are the most massive, coherent structures in the universe. A typical filament spans hundreds of megaparsecs in length and only a few megaparsecs in width, threading through the space between voids like a river between planes along its length. Matter accumulated from both sides as adjacent voids evacuated their interiors. The gas in filaments spans a wide range of temperature and density. In the hottest, densest regions near cluster nodes, the gas is heated to tens of millions of degrees by gravitational compression and shock heating visible in X-ray observations as the warm hot intergalactic medium. In the cooler, less dense regions of filament walls, the gas is warm but not X-ray luminous. Big Bang nucleosynthesis, the process by which protons and neutrons combined into light atomic nuclei in the first minutes after the Big Bang, predicted the total abundance of ordinary matter with high precision, roughly 5% of the total mass energy content. But when astronomers tallied up all the ordinary matter they could actually detect in stars, in galaxies, in cold intergalactic gas, in galaxy clusters, the sum fell short by a substantial factor. The missing baryons were eventually tracked down in the late 2010s through multiple independent observations of the warm hot filament gas, the intergalactic medium at temperatures between 10,000 and 10 million Kelvin, filling the filaments of the cosmic web. The missing baryons were not missing from the universe. They were hiding in the web, invisible to the surveys that had looked only in galaxies and clusters. The cosmic web is not merely a skeleton of dark matter and galaxies. It is a warm, diffuse, chemically enriched medium filling the connections between galaxy clusters, the largest coherent reservoir of ordinary matter in the universe. Understanding how these structures formed required more than observation. It required simulation. The cosmic web that astronomers were mapping had to have emerged from somewhere. Its origin lay in the earliest moments of the universe, in processes so remote in time that they can only be accessed through their consequences. The story begins with inflation. The brief period of exponential expansion thought to have preceded the hot Big Bang, during which the universe grew from a region smaller than a proton to a volume larger than the currently observable cosmos in a fraction of a second, roughly 10 to the negative 32 seconds. Inflation was proposed in 1980 by Alan Guth, and independently and in more refined forms by Andre Linde and by Paul Steinhardt and Andreas Albrecht. The driving motivation was to solve several puzzles in standard Big Bang cosmology that the simple model could not address. Why the cosmic microwave background is so uniform across regions that should never have been in causal contact. Why the spatial geometry of the universe is so precisely flat. Why no magnetic monopoles or other exotic relics have been detected. Inflation solves all three by postulating that the observable universe expanded from a tiny causally connected region, that the rapid expansion diluted any curvature and any exotic particles, and that the nearly uniform temperature of the microwave background reflects the nearly uniform conditions of the pre-inflationary patch. But inflation introduces a feature that goes beyond these solutions. It takes quantum fluctuations, random, unavoidable variations in the energy of the inflaton field that drove inflation, and stretches them to macroscopic scales. A quantum fluctuation that would normally exist only at subatomic scales, lasting for a tiny fraction of a second before disappearing, is instead stretched by the exponential expansion to scales far exceeding the Hubble radius of the inflating universe. Once stretched to those scales, the fluctuation can no longer oscillate back. It is frozen in place, imprinted on the density of space as a permanent variation. These frozen fluctuations are the seeds from which all subsequent structure grew. They are also the temperature fluctuations measured in the cosmic microwave background, the faint patterns of slightly hotter and slightly cooler regions that the blub map and blank mapped with extraordinary precision and from which cosmological parameters are derived. The predictions of inflation for the statistical properties of these fluctuations, their amplitude, their scale dependence, their lack of preferred direction, match the observed microwave background in detail. Inflation predicts a nearly scale invariant spectrum of fluctuations with slightly more power on large scales than small. It predicts Gaussian statistics. The fluctuations are drawn from a random distribution with no preferred values, no preferred directions, no characteristic scale. It predicts a specific relationship between the temperature fluctuations and the polarization pattern in the microwave background. All of these predictions have been confirmed by Planck and its predecessors. After inflation ended and the hot Big Bang began the reheating phase, during which the energy of the inflaton field was transferred into a hot plasma of fundamental particles, the universe was filled with a soup of quarks, leptons, photons, and the as yet unidentified dark matter particles. For the first few minutes, the temperature was high enough for nuclear reactions. Protons and neutrons combined to form helium-4, deuterium helium-3 and traces of lithium, the light elements synthesized in Big Bang nucleosynthesis. After the first few minutes, the temperature dropped below the threshold for nuclear reactions and the elemental composition of the universe was fixed. Roughly 75% hydrogen, 25% helium by mass with trace quantities of everything else. For the next 380,000 years, the universe was a dense hot plasma in which photons and ordinary matter were tightly coupled. Light could not travel freely. It was constantly absorbed and re-emitted by the dense plasma, carrying matter along with it. Sound waves, acoustic oscillations driven by the competition between the gravity of overdense regions pulling matter inward and the radiation pressure of the photon-baryon plasma pushing it outward, propagated through this medium, carrying the density variations left by inflation. When the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, the epoch of recombination, the plasma suddenly became transparent. The photons decoupled from the matter and streamed freely outward in all directions. These are the photons we detect today as the cosmic microwave background, their wavelengths stretched by a factor of roughly 1000 by the subsequent expansion. The matter they left behind was free for the first time to evolve under gravity alone. The scale to which those acoustic waves had propagated before stopping the sound horizon, roughly 150 megaparsecs, was imprinted in the distribution of matter as a preferred clustering length. The baryon acoustic oscillation scale. It remains detectable today in the distribution of galaxies. If you measure the separation between all pairs of galaxies in a large survey, you find a slight excess of pairs separated by exactly that distance, a faint echo of the acoustic oscillations preserved across 14 billion years of cosmic evolution. This feature has been detected in multiple surveys and used to measure the expansion history of the universe with high precision. It is one of the pillars of modern cosmological evidence. After recombination with the photon pressure gone, gravity took over entirely. The first structures to collapse were the smallest overdense regions, small halos of dark matter, each perhaps 1 million solar masses in total, that had been held in check by radiation pressure during the plasma era and could now contract freely. These first halos formed perhaps 100 million years after the Big Bang, and within them the first stars ignited. This population tree stars, so called because they formed entirely from the primordial hydrogen and helium of the Big Bang, with essentially no heavier elements, were likely very massive, perhaps hundreds of solar masses, burning hot and bright for only a few million years before dying in violent supernovae or collapsing directly into black holes. Their short lives and their deaths enriched the surrounding gas with the first heavy elements ever produced outside the Big Bang: carbon, oxygen, silicon, iron. The second generation of stars formed in this enriched gas, and each subsequent generation of stars built upon the elemental legacy of its predecessors. The ultraviolet radiation from the first stars began reionizing the surrounding neutral hydrogen, carving expanding bubbles of ionized gas. As more stars and galaxies formed, more ionizing radiation was produced, and the bubbles expanded and merged. The epoch of reionization, the period during which the universe transitioned from a neutral to an ionized state, lasted from roughly 200 million to 1 billion years after the Big Bang. It was the last major phase transition in the history of the universe, and it left imprints in the distribution of neutral hydrogen that future radio telescopes, particularly the Square Kilometre Array, currently under construction in South Africa and Australia, will map in 3 dimensions, providing a direct observational window into the era when the first structures were illuminating the cosmic dark. The large-scale void and filament structure we observe today began forming during this same epoch. Dark matter, which had not been coupled to the radiation pressure during the plasma era and had therefore been free to cluster even before recombination, led the assembly. Its distribution set by the original inflationary fluctuations, modified by the acoustic oscillations during the plasma era, defined the gravitational potential landscape into which everything else fell. Where the dark matter density was high, ordinary gas cooled and condensed, forming the first galaxies. Where it was low, matter was gravitationally evacuated toward the surrounding denser regions, leaving behind the protovoids that would grow over billions of years into the supervoids we observe today. In 2005, a collaboration of researchers unveiled the Millennium Simulation, a computational model of cosmic evolution tracking the gravitational interactions of 10 billion simulated dark matter particles inside a cube equivalent to 2 billion light-years across. The simulation was initialized at a redshift of 127, roughly 22 million years after the Big Bang, using initial conditions derived from the DEWMAP satellite's measurements of the cosmic microwave background, then run forward to the present day. The computation required weeks on the supercomputer facilities of the Max Planck Society in Garching, Germany. Galaxy clusters, filaments, and voids all emerged naturally from the initial conditions, without any parameter tuning beyond the basic cosmological model. Subsequent simulations Illustristen G e egal Simba Horizon X en added the physics of ordinary matter, gas cooling and star formation, stellar feedback, black hole accretion and feedback, chemical enrichment. These so-called hydrodynamical simulations produce simulated universes that can be directly compared to observations, simulated galaxy catalogs, simulated X-ray maps of cluster gas, simulated spectra of background quasars absorbed by intergalactic gas. The agreement between simulation and observation where it exists represents one of the most remarkable achievements of computational astrophysics. The mechanism that drove the formation of these structures was not ordinary matter alone. The dominant ingredient was dark matter, a substance that does not emit or absorb electromagnetic radiation, cannot be seen directly by any instrument, and reveals itself only through its gravitational influence. Dark matter constitutes roughly a quarter of the total mass energy content of the universe. Ordinary matter, the atoms, molecules, gas, and stars that compose everything we have ever directly detected, accounts for only about 5%. The remaining 70% is dark energy, the name given to the property of space that drives the accelerating expansion of the universe, Discovered in 1998 when two independent teams studying distant Type Ia supernovae found that the universe's expansion was not slowing down as gravity should dictate, but speeding up. Sol Perlmutter, Brian Schmidt, and Adam Rees received the Nobel Prize in Physics in 2011 for this discovery. Dark energy is most simply modeled as a cosmological constant, Einstein's lambda, a uniform energy density permeating empty space that produces a repulsive pressure. In this simplest model, dark energy is static. Its density does not change as the universe expands. Alternative models allow dark energy to vary over time, phantom energy, quintessence, scalar fields rolling down an energy landscape, and distinguishing between these alternatives from observational data is one of the primary scientific goals of the current generation of cosmological surveys. Recent results from the Dark Energy Spectroscopic Instrument, analyzing baryon acoustic oscillations across a large galaxy sample in 2024, found weak hints that dark energy's equation of state parameter may be evolving over cosmic time, not a confirmed detection, but a tension with the simplest model that future data will either amplify or erase. Between dark matter and dark energy, everything visible is a minority report. A thin layer of luminous material wrapped around an invisible scaffolding, driven apart by a force we cannot directly detect. Understanding the nature of these two invisible components is the central challenge of contemporary cosmology. The cosmic web, that vast network of filaments and sheets and bubbles, is, in the deepest sense, a map of dark matter's gravitational memory across 14 billion years of cosmic history. The nature of dark matter remains one of the deepest unsolved problems in physics. In the 1930s, Fritz Zwicky measured the velocities of galaxies in the Coma cluster and found that they were moving far too fast to be bound by the visible mass of the cluster. The cluster should have flown apart long ago, unless there was far more mass than could be seen. In the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies, the velocity of stars and gas as a function of their distance from the galactic center, and found that they did not fall off with increasing radius as Newton's laws predicted for a system where most of the mass was in the luminous center. Instead, the curves were flat. Stars at the outer edges of galaxies moved as fast as stars near the center, implying the existence of an extended invisible halo of mass surrounding each galaxy. These and other lines of evidence accumulated over decades into a compelling case that the universe contains far more gravitating matter than can be detected through any form of electromagnetic radiation. The matter exists, we feel its gravity. We simply cannot see it. Researchers have proposed dozens of candidate particles for dark matter. The most studied class is weakly interacting massive particles, or WIMPs, hypothetical particles with masses in the range of 10 to 1,000 times the proton mass, interacting with ordinary matter only through the weak nuclear force and gravity. WIMPs arise naturally in supersymmetric extensions of the standard model of particle physics, which predict the existence of a stable, lightest supersymmetric particle for reasons entirely independent of the dark matter problem. This independent motivation lent the WIMP hypothesis an appealing theoretical economy. It would solve two problems at once: underground detectors built in former mines, the Lux-Zeppelin experiment in the Homestake mine in South Dakota, with its 10 tons of liquid xenon, the Pandex 4T experiment in China's Jinping underground laboratory, deepest underground laboratory in the world by overburden, have searched for the faint nuclear recoil signatures that a passing WIMP might leave, shielded from cosmic ray interference by kilometers of rock. They have found nothing. The exclusion limits on WIMP-nucleon interaction cross-sections have improved by many orders of magnitude over the past 3 decades, ruling out most of the theoretically favored parameter space. LHC experiments at CERN have found no supersymmetric particles at the energies accessible to the machine. The simplest WIMP models are under severe pressure, though more complex supersymmetric scenarios with different mass spectra and interaction structures remain viable. Another candidate is the axion, an extraordinarily light particle first proposed by Helen Quinn and Roberto Pecce in 1977 as a solution to the strong CP problem in quantum chromodynamics. The puzzle of why the strong nuclear force does not appear to violate the symmetry between matter and antimatter, even though its equations permit it to do so. Axions, if they exist, would be produced abundantly in the early universe through a process called the misalignment mechanism, accumulating in a coherent quantum state, a Bose-Einstein condensate of sorts that would behave precisely like dark matter on cosmological scales. Axion detection experiments use resonant microwave cavities immersed in strong magnetic fields, in which an axion crossing the detector converts into a microwave photon through the inverse Primakov effect. The ADMX experiment at the University of Washington and the Haystack experiment at Yale are searching for axions in different mass ranges. No confirmed axion signal has yet been found, though the experiments are gradually probing the theoretically motivated range of axion masses and coupling constants. A third candidate class is sterile neutrinos, hypothetical heavier cousins of the standard model neutrinos that mix with ordinary neutrinos but interact only through gravity, not through the weak force. They would be produced in the early universe through oscillation from ordinary neutrinos and could account for dark matter if they have masses in the Kev range. X-ray telescopes have searched for the spectral line that would be produced when sterile neutrinos decay, and the candidate signal at 3.5 keV was reported in 2014 in observations of the Perseus cluster and the Andromeda galaxy. The signal has been contested. Some analyses confirm it. Others find it consistent with background, and the XRISM X-ray telescope launched in 2023 is providing definitive measurements of the Perseus cluster spectrum that should resolve the dispute. Primordial black holes formed from density fluctuations in the very early universe, constitute another candidate. Gravitational wave observations from LIGO and Virgo constrain their abundance in certain mass ranges. But windows remain open, particularly for black holes with masses between a fraction of a solar mass and a few hundred solar masses. What all these searches share is a fundamental uncertainty. We do not know what dark matter is, and we may not find out for decades or at all. The universe reveals its composition through its gravitational effects, but conceals its fundamental nature behind a veil of invisibility. We know dark matter is there. We feel it, we map it through gravitational lensing, through galaxy rotation curves, through the thermal properties of the cosmic microwave background, through the clustering of galaxies, through the growth of structure across cosmic time. Its fingerprints are everywhere, but the particle or particles or whatever other physical entity it represents remains elusive. Even the voids themselves are not entirely empty. Observations have confirmed that the near-vacuum regions between galaxy filaments contain protogalactic clouds, immense reservoirs of gas and dust in the early stages of galaxy formation. The galaxies that do exist inside voids are a distinct population from their counterparts in denser environments. They tend to be smaller. They tend to be bluer, actively forming new stars, since without the gravitational harassment of close neighbors, their gas supply has not been stripped away or heated to temperatures that suppress star formation. They tend to be more isolated, with fewer satellite galaxies, and their morphologies are often simpler, late-type spirals and irregulars, with little evidence of the merger-driven morphological transformation that shapes galaxies in dense clusters. Studies of void galaxies using the Sloan Digital Sky Survey have confirmed that they are systematically younger, less metal-enriched, and more star-forming than galaxies in filaments and clusters of equivalent mass. The void environment is, in effect, a slow-motion universe. Everything happens on longer timescales, with less environmental pressure in quieter cosmic conditions. The physics of galaxy clusters, the densest nodes of the cosmic web, illuminates the properties of the surrounding voids by contrast. A massive galaxy cluster like the Coma cluster, located about 300 million light-years from Earth in the constellation Coma Berenices, contains thousands of member galaxies embedded in a hot plasma of ionized gas 10 times more massive than all the stars in all the galaxies combined. All of this embedded in a dark matter halo 50 times more massive than the gas, extending to radii of several megaparsecs. The cluster's total mass approaches 10 quadrillion solar masses. It formed through the hierarchical merging of smaller halos over billions of years, each merger heating the gas through shocks and turbulence, each merger adding galaxies to the growing collection. The galaxy population in the Coma cluster is predominantly old, red, and passive, their star formation long since quenched by the hostile cluster environment. Cold gas has been stripped from infalling galaxies by the ram pressure of the hot intracluster medium. Galaxy-galaxy interactions and gravitational tidal forces have transformed spirals into lenticulars and irregulars into ellipticals. The cluster is, in a sense, the end state of a galaxy's environmental evolution, a place where the raw material of galaxy formation has been exhausted and the stars that remain can only age and fade. Galaxies in the cluster outskirts, the infall region, where matter is still flowing from the surrounding filaments into the cluster's gravitational well, show intermediate properties. They are more star-forming than cluster core galaxies, but less so than filled galaxies in voids. Their star formation is being gradually suppressed as they approach the cluster, losing cold gas to the increasingly dense intracluster medium. This gradient of galaxy properties, from cluster core to filament, to void wall to void interior, from the red, passive, environmentally processed galaxies of clusters to the blue, active, undisturbed galaxies of voids, traces the gravitational history of the matter that now inhabits each environment. Each galaxy carries the record of where it has been and what it has experienced in the form of its stellar population, its morphology, its gas content, and its color. Weak gravitational lensing provides a way to map the matter distribution, including the dark matter that galaxies trace only imperfectly across the cosmic web without relying on any assumption about how galaxies trace dark matter. When photons from a distant galaxy travel toward us, they pass through the inhomogeneous matter distribution of the intervening universe. Each mass concentration along the line of sight slightly deflects the photon paths, distorting the apparent shape of the background galaxy, making it appear slightly more elongated in one direction than it would be in the absence of the lensing mass. This distortion is tiny, a few percent in the most favorable cases, and undetectable in any individual galaxy because galaxies have intrinsic ellipticities that are orders of magnitude larger. But the distortion is correlated across the sky. All background galaxies in the same angular neighborhood are distorted in the same direction by the same foreground mass concentrations. By averaging the shapes of millions of background galaxies and looking for spatial correlations in their orientations, weak lensing surveys can reconstruct the projected mass distribution, the dark matter map of the universe along the line of sight. The kilodegree survey, the dark energy survey, and the Hypersuprime Chem Subaru strategic program have each produced weak lensing maps of substantial fractions of the sky, revealing the distribution of dark matter in filaments and clusters and its absence in voids. These maps are compared to the predictions of lambda CDM, specifically to the predicted sigma-8 parameter, the amplitude of matter clustering on a scale of 8 megaparsecs, and the comparison has revealed the sigma-8 tension. Lensing surveys consistently find a slightly lower amplitude of matter clustering than predicted from the Planck microwave background analysis, with a discrepancy of 2 to 3 sigma. Whether this tension reflects systematic errors in lensing shape measurements, intrinsic alignments of galaxy shapes that mimic the lensing signal point spread function calibration errors, or genuine physics beyond lambda CDM, is actively debated. Euclid and the Vera Rubin Observatory will produce weak lensing maps of such quality that the systematic errors will either be eliminated or made manifest, providing a definitive answer to the sigma-8 question. Light passing through voids also behaves strangely. The paths of photons from distant quasars and galaxies are measurably distorted when they cross void regions, in ways that cannot be fully explained by ordinary refraction or the imperfections of any telescope. This residual gravitational lensing, the bending of light by the dark matter that even voids contain, provides an independent probe of the matter distribution. Additionally, photons crossing a void experience a shift in their energy due to the expansion of the universe during their transit. The integrated Sachs-Wolf effect imprints a faint temperature signature on the cosmic microwave background, slightly cooler in the directions of voids and slightly warmer in the directions of galaxy clusters. This effect has been detected statistically by cross-correlating maps of galaxy positions with maps of the microwave background temperature, providing direct evidence for dark energy. It is the accelerating expansion of space that prevents the photons from recovering their full energy upon exiting the void. A universe without dark energy would show no integrated Sachs-Wolf signal. The observation confirms that voids are actively expanding under the influence of dark energy, emptying faster than gravity alone would drive. Gravitational lensing, the bending of light by mass, operates not only as a tool for mapping the dark matter in the cosmic web, but also as a natural cosmic telescope that magnifies distant objects. When a massive galaxy cluster lies between us and a more distant background galaxy, the cluster's gravity bends the light paths from the background galaxy around it, creating multiple distorted images, arcs, rings, or multiple point-like images depending on the geometry. This strong gravitational lensing can magnify the background galaxy by factors of 10, 50, or even 100. Making it possible to observe in detail objects that would otherwise be far too faint to study. Webb has exploited strong lensing clusters as cosmic magnifiers to observe galaxies in the very early universe with far greater detail than would otherwise be possible. The Sunrise Arc, a galaxy at a redshift of approximately 6 that is lensed by a galaxy cluster, has been magnified to the point where individual star-forming regions within it, compact knots of young, hot stars, are resolvable by Webb's instruments. These images provide a window into the internal structure of early galaxies that no direct observation could currently match. Statistical weak lensing, the use of the correlated distortions of millions of faint background galaxies to map the projected mass distribution, provides complementary information. Void profiles in weak lensing maps are particularly informative. The lensing signal around voids is expected to be negative. Voids are mass deficient, so they produce a slight anti-lensing effect that demagnifies background sources rather than magnifying them. Detecting and characterizing void lensing profiles allows direct measurement of the matter under density in voids independent of galaxy number counts and free of the assumption that galaxies trace mass proportionally. The kilodegree survey and the dark energy survey have both measured void lensing signals in their weak lensing data, confirming that voids are genuinely underdays in total matter. Not merely in galaxies, and that the underdensity profiles match the predictions of the standard cosmological model reasonably well, with residuals that may reflect the sigma-A tension. The use of voids as cosmological probes extends beyond their size distribution and lensing profiles. The redshift space distortions. The anisotropic distortion of the void shape in redshift space, caused by the peculiar velocities of galaxies flowing outward from the void, provide a measurement of the growth rate of structure. In real space, a void is approximately spherical. In redshift space, the space defined by the measured redshift rather than the true distance, the same void appears flattened or elongated depending on whether its surrounding galaxies are flowing outward as expected for a real void or inward as expected for an overdense region. The precise shape of voids in redshift space, compared to the expected spherical shape in real space, provides a clean measurement of the ratio of the growth rate of structure to the Hubble constant, a quantity sensitive to the dark energy equation of state and to modifications of general relativity. This technique, called void redshift space distortions, has been applied to Sloan Digital Sky Survey data and BOSS data, providing independent constraints on growth rate that complement those from galaxy-galaxy redshift space distortions. Future applications to DESI and Euclid data will substantially sharpen these constraints. Void autocorrelation and cross-correlation statistics, the way voids cluster with each other and with galaxy overdensities, provide yet more information. The void-galaxy cross-correlation function, measuring how galaxy number density varies as a function of distance from void centers, is a direct measurement of the density profile of voids and their surrounding structures. The void-void correlation function, measuring how voids cluster with respect to each other, probes the large-scale environment of voids. On very large scales, voids tend to be surrounded by overdense walls and filaments, and their two-point correlation reflects the underlying matter-power spectrum on those scales. The use of voids as tracers of the large-scale matter distribution, analogous to but complementary to the use of galaxies, opens up statistical probes that are less affected by nonlinear clustering effects than galaxy statistics, potentially providing cleaner cosmological information in the scales between the quasi-linear and fully nonlinear regimes. Now comes the detail that reorients everything. We live inside a void, not at the edge of one, not in a galaxy that happens to be drifting toward one inside, embedded within the interior of the largest known underdense region in the observable universe. The evidence for this was assembled gradually over 3 decades, beginning with Brent Tully and Richard Fisher's identification of the local void in 1987, deepened by subsequent peculiar velocity surveys, and crystallized in 2013 when a team led by Ryan Kinnan, Amy Barger, and Lennox Cowie used deep photometric and spectroscopic surveys to map the galaxy number density around the Milky Way to distances of several hundred megaparsecs. Their analysis found a systematic deficiency of galaxies in all directions, at distances between about 100 and 300 megaparsecs from us, a deficiency indicating that we sit near the center of a vast underdense region. This structure, the KBC void, spans approximately 2 billion light-years in diameter. Our galaxy lies within a few 100 million light-years of its center, near enough that for most observational purposes we are embedded within it. The KBC void dwarfs everything previously identified. The Eridanus supervoid, which troubled cosmologists for its anomalous size, spans roughly 1 billion light-years. The APLP36 underdense region spans roughly 400 megaparsecs. The Boots void, which astonished the community in 1981, spans 60 megaparsecs. The KBC void spans roughly 600 megaparsecs. The difference in scale is not merely quantitative. It is the kind of difference that changes how you interpret every observation made from within it. The existence of a locally underdense environment around the Milky Way had been suspected since Tully and Fisher's original 1987 work, though in a more modest form. What Toney and Fisher called the local void was a region of underdensity extending perhaps a few 100 million light-years in certain directions, first inferred from asymmetries in the peculiar velocity field of nearby galaxies. The local void was difficult to study in detail because its nearest boundary lies in the direction of the galactic center, a direction obscured by the dense gas and dust of the Milky Way's own disk, which absorbs optical light from extragalactic sources. The region became known as the zone of avoidance, a strip of sky where the Milky Way renders the universe behind it nearly invisible to optical surveys. Radio surveys, which are insensitive to dust extinction, later penetrated the zone of avoidance and confirmed that the underdeath region extended beyond what early optical surveys could measure. Infrared surveys from space, the IRES All-Sky Survey in the 1980s and the 2MES All-Sky Survey in the early 2000s, mapped the galaxy distribution in those obscure directions and confirmed the outflow signature of the local void. Toney later led the Cosmic Flows program, a systematic effort to compile the most comprehensive and accurate catalogue of galaxy peculiar velocities, measuring the distances and velocities of tens of thousands of galaxies using multiple distance indicators applied consistently across the full sky, including the Toney-Fisher relation for spirals, surface brightness fluctuations for ellipticals, and the fundamental plane relation. Cosmic Flows 3 included roughly 18,000 galaxy distances. Cosmic Flows 4, published in 2022, extended this to about 56,000. The velocity field derived from these data reveals the cosmic web in unprecedented detail, where matter is falling inward toward attractors, where it is flowing outward from voids. Galaxy superclusters had been identified since the 1950s, when Gerard de Vaucouleurs first described the local supercluster now known as the Virgo supercluster, but superclusters lacked a rigorous physical definition. A cluster of galaxies is gravitationally bound. Its member galaxies orbit their common center of mass and will not escape on any timescale. A supercluster is not. The galaxies of a supercluster are not mutually bound. They are simply close enough in space to be statistically associated. The question of where one supercluster ends and another begins had no clean physical answer, until Toney's team proposed using the velocity field itself as the definition. A supercluster, they argued, should be defined as the set of all galaxies whose peculiar velocities converge toward a common basin of gravitational attraction, the region of space from which galaxies flow inward rather than outward. By this definition, Laniakea is a precisely defined object. Every galaxy within it is at the present moment falling toward the great attractor region, not toward the attractors of adjacent basins. The boundary of Laniakea is a gravitational divide, a ridge in the cosmic velocity field where matter is in a state of equilibrium between competing attractors, rather than an arbitrary density threshold. By this definition, Laniakea contains roughly 100,000 galaxies, spans approximately 500 megaparsecs, and has a total mass on the order of 10 to the power of 17 solar masses. The Milky Way sits near its outer rim, roughly 2/3 of the way from the center to the boundary, in the direction away from the great attractor. Our galaxy is not at the center of Laniakea, it is near its periphery, close to the boundary with the adjacent Perseus-Pisces supercluster basin. The great attractor itself, the gravitational anomaly toward which the Milky Way, Andromeda, the Virgo cluster, and the rest of Laniakea are flowing, is located in the direction of the constellation Centaurus, partially hidden behind the zone of avoidance. Early analysis in the 1980s detected the anomalous bulk flow of nearby galaxies in that direction and inferred a massive concentration of matter responsible for it. The dominant contributor now identified is the Norma cluster, a rich galaxy cluster at a distance of roughly 70 megaparsecs, combined with the broader Shapley supercluster beyond it at roughly 200 megaparsecs. The Shapley supercluster is one of the largest concentrations of galaxies in the observable universe. a massive supercluster containing dozens of galaxy clusters with a total mass comparable to Laniakea itself. It exerts a gravitational pull on our supercluster that is detectable in the peculiar velocities of thousands of galaxies across a large fraction of the sky. Eventually, on timescales of tens of billions of years, the Milky Way and its local group neighbors will be carried toward the Shapley supercluster by this attraction, even as the accelerating expansion of the universe pushes more and more distant structures beyond reach. All of this motion occurs within the interior of the KBC void. The local group flows outward from the void's center toward the denser walls that border it. Simultaneously, it flows toward the Great Attractor and the Shapley supercluster. These two motions are not exactly aligned. They pull in somewhat different directions, and the total peculiar velocity of the Milky Way relative to the cosmic microwave background rest frame, roughly 600 kilometers per second in the direction of the constellation Centaurus, reflects their combined influence. Every galaxy in the local universe is moving under the competing gravitational pulls of nearby attractors and the outward flow from nearby voids. Disentangling these contributions is a central challenge of peculiar velocity cosmology, and it requires the comprehensive data of surveys like cosmic flows. And this has consequences, real, measurable, unresolved consequences. For nearly a century, the rate at which the universe expands has been described by a single number known as the Hubble constant, the increment of recession velocity added for each unit of distance between any 2 points in the universe. Edwin Hubble himself derived the first estimate in 1929 using the velocities and distances of nearby galaxies. His value, approximately 500 kilometers per second per megaparsec, was wrong by a factor of 7. The distances he used were poorly calibrated. His Sepheid variable stars were confused with a different, intrinsically dimmer class of variable, leading to systematic underestimates of distance and corresponding overestimates of the expansion rate. A century of refinement followed. The true value converged gradually over decades toward the now contested range of 67 to 73. Measuring the Hubble constant accurately depends critically on which rung of the cosmic distance ladder you stand on. The distance ladder is a hierarchical system of overlapping distance indicators, each calibrated against the previous one. At the base, parallax measurements of nearby stars, where the apparent shift of a star against the background as Earth orbits the Sun provides a direct geometric distance. These calibrate Cepheid variable stars, pulsating giants whose oscillation period is related to their intrinsic luminosity by a well-established empirical law discovered by Henrietta Swan Leavitt in 1908 in the Milky Way and nearby galaxies. Cepheids calibrate type Ia supernovae, thermonuclear explosions of white dwarf stars that reach a standard peak luminosity, making them visible across billions of light years. And the supernovae provide distances to galaxies far enough away that their recession velocities are dominated by the cosmological expansion rather than by local gravitational perturbations. Each rung of this ladder introduces its own uncertainties, and the uncertainties compound. But the Hubble Space Telescope and more recently the James Webb Space Telescope have measured Cepheid distances to more than 50 galaxies that have also hosted observed supernovae, anchoring the calibration with extraordinary precision. The result? 73 kilometers per second per megaparsec, with an uncertainty of roughly 2%. The early universe measurement uses an entirely different approach. The cosmic microwave background encodes the acoustic oscillation scale, the baryon acoustic scale, as a precise ruler whose physical length can be calculated from first principles, given the matter and radiation density of the universe at recombination. Measuring the apparent angular size of this feature in the microwave background map gives the angular diameter distance to the surface of last scattering, and combining this with the known physical scale gives the expansion history from recombination to the present. The Planck satellite measured this with remarkable precision, yielding 67 kilometers per second per megaparsec with an uncertainty of roughly 1%. This measurement is entirely independent of the distance ladder. It uses no Cepheids, no supernovae, no empirical calibrations. It relies only on well-understood physics of the early universe and a precisely measured microwave background map. The two values, 67 and 73, differ by about 9%. The combined uncertainty on the difference is roughly 5 to 6 times the combined 1 sigma uncertainty, 5 to 6 sigma of statistical significance. In particle physics, 5 sigma is the conventional threshold for claiming a discovery. In cosmology, it is the threshold for a crisis. The Hubble tension is not a rounding error. It has been confirmed by multiple independent analyses using different galaxy samples, different distance indicators, and different analysis pipelines. It persists across different redshift ranges. It persists in gravitational lens time delay measurements, which use the different arrival times of multiple images of the same quasar to measure the Hubble constant independently of both the distance ladder and the microwave background, arriving at a value of roughly 73. It persists in measurements using the tip of the red giant branch, a different stellar standard candle, calibrated against the Large Magellanic Cloud distance measured by eclipsing binary stars, which gives a result of approximately 70 as well. Proposed solutions fall into several categories. Early dark energy, a component that behaves differently from the cosmological constant before recombination, active only in the first 100,000 years of the universe, can shift the acoustic scale in the early universe and thereby change the Hubble constant inferred from the microwave background, potentially reconciling the two measurements. The challenge is that introducing early dark energy generically worsens other tensions, such as the sigma-8 tension, and requires careful tuning of the early dark energy parameters to avoid conflicting with other observational constraints. Self-interacting dark matter with forces acting on it beyond gravity can alter the growth of structure in ways that affect the Barbarian acoustic scale, potentially providing an alternative path to resolution. Interacting dark energy that exchanges energy or momentum with dark matter, changes the expansion history in a different way and has been explored extensively as a solution. Decaying dark matter, in which a fraction of dark matter decays into some lighter invisible product, changes the matter density between recombination and today in a controlled way. Extra neutrino species, adding to the total radiation density during the plasma era, shift the acoustic scale and have long been a simple proposed solution, but constraints from other observations on the effective number of neutrino species are now tight enough to disfavor this option. One candidate explanation that requires no new physics, only acknowledgement of our observed cosmic environment, is the KBC void. A galaxy inside a large underdeath region experiences less gravitational braking from the surrounding mass distribution than a galaxy in a typical patch of universe. The low density of matter in the void's interior means fewer gravitational obstacles to outward flow. This systematic outward flow adds a component to the recession velocities of nearby galaxies that looks from inside the void like a higher than average expansion rate. Estimates from peculiar velocity field models suggest the effect could inflate local Hubble measurements by as much as 11% relative to the global value. In 2020, researchers recalculated the void's influence using updated models of its density profile and peculiar velocity field and found that it could account for a significant fraction of the observed tension. Comparisons with cosmic flows for data confirmed the basic prediction. The universe may not be internally inconsistent. We may simply be measuring expansion from inside a bubble and interpreting our local environment as universal modified Newtonian dynamics. MOND, proposed by Mordechai Milgram in 1983, alters gravity at very low accelerations, making it effectively stronger at the low accelerations characteristic of the outer regions of galaxies and the interior of galaxy clusters. In its original form, MOND explains galaxy rotation curves without dark matter and makes predictions about galaxy dynamics in low acceleration environments. In relativistic extensions, particularly the tensor vector scalar gravity theory developed by Jacob Bekenstein and its successors, MOND predicts different growth rates for cosmic structure than lambda CDM, potentially tolerating the existence of larger underdense regions. Whether MOND survives observational tests from galaxy cluster dynamics, the bullet cluster of galaxies, and the dynamics of high redshift galaxies observed by Webb remains genuinely contested. Some authors argue the bullet cluster definitively rules out MOND. Others dispute this. The debate continues. The Hubble tension, at its core, represents the possibility that the standard cosmological model, lambda CDM, tested against thousands of independent observations, the most precisely confirmed physical theory ever applied to the universe as a whole, may be missing something, not something large. The model's successes are real and extensive, but something subtle, detectable now only because measurements have finally achieved the sub-percent precision required to see it. Resolving the tension will likely require either the discovery of a systematic error in current measurements, the confirmation of new physics beyond lambda CDM, or some combination of both. Future surveys, DESI, Euclid, the Vera Rubin Observatory, the CMB S4 ground-based telescope array, the Nancy Grace Roman Space Telescope, will sharpen both the early universe and late universe measurements, either revealing the tension more clearly or showing the way to its resolution. While cosmologists debate the nature of our local environment, a different kind of challenge has arrived from orbit. The James Webb Space Telescope, launched in December 2021 and reaching full scientific operations in mid-2022, was designed specifically to observe the very first galaxies, the earliest structures that coalesced from primordial gas after the Big Bang, in the infrared wavelengths that earlier instruments could not effectively access. At the high redshifts corresponding to galaxies more than 13 billion light-years away, even optical light from the source has been stretched by cosmic expansion into the infrared. Only an infrared telescope with sufficient collecting area and a detector sufficiently cold and sensitive could see these objects clearly. Webb sees them with a clarity that no previous instrument approached. Its primary mirror, 6.5 meters in diameter, is composed of 18 gold-plated beryllium hexagons, whose shapes are individually adjustable by tiny actuators to maintain the mirror's precise curvature against the temperature swings of space. It operates at the second Lagrange point of the Earth-Sun system, 1.5 million kilometers from Earth in the anti-Sun direction, where the gravitational forces of Earth and Sun combine to maintain the spacecraft in a stable orbit. The 5-layer sun shield, each layer thinner than a human hair, but together reducing the solar heat load by a factor of 1,000,000, keeps the telescope and its instruments near 7 Kelvin. Cold enough to eliminate the thermal noise that would otherwise drown out the faint infrared glow of distant galaxies. The total cost of the mission exceeded $10 billion and involved agencies from 3 continents. It is the most expensive science instrument ever built, and it has not disappointed. The standard hierarchical model of galaxy formation held that the early universe should contain mostly small, irregular, chaotic protogalaxies, the building blocks of larger structures, slowly assembling through mergers and collisions into the ordered spirals and massive ellipticals we see in the local universe today. This picture was supported by the theoretical expectation that structure grows from small to large. Dark matter halos accumulate mass through mergers, gas falls into deepening potential wells, The first stars ignite in compact clumps. Those clumps merge and grow, and galaxies gradually acquire their mass and their morphological regularity over billions of years. Hubble's deep-field images broadly supported this picture. At high redshift, galaxies appeared smaller, clumpier, and more irregular than nearby ones. The familiar Hubble sequence, spirals, lenticulars, ellipticals, irregulars, seemed to fade with look-back time, replaced by irregular patches of light that bore little resemblance to the stately objects visible in the local universe. Webb disagrees repeatedly and insistently. A large international team that analyzed nearly 4,000 galaxies imaged by Webb found that the distribution of morphological types differs dramatically from what Hubble suggested. Where Hubble classified roughly 10% of high redshift galaxies as spiral, Webb classifies 60% regular structured galaxies, the kind we assume took billions of years to assemble, appear to have existed much earlier than the model predicts. This revision is not a small adjustment. Among galaxies with stellar masses greater than 1 billion solar masses, the fraction of each morphological type shows remarkably little variation across redshift in Webb's data. Spirals are approximately as common at redshift 2, when the universe was about 3 billion years old as they are today. This contradicts every major model of galaxy formation published before Webb's launch. Part of this discrepancy reflects instrumental improvements. Webb's primary mirror collects nearly 7 times as much light as Hubble's, providing superior angular resolution and sensitivity. Part reflects the physics of observation in the infrared. Longer wavelengths pass through a galaxy's own interstellar dust more easily, revealing the underlying stellar structure without the obscuring effects that make optical images appear clumpier. A spiral galaxy that appears irregular in blue light, because dust along its spiral arms absorbs and scatters the starlight, may appear clearly spiral in the infrared, where the dust is largely transparent. Hubble, working primarily in optical and near-ultraviolet light, was systematically biased towards seeing disorder in dust-rich young galaxies. Webb removes this bias, but the magnitude of the revision exceeds what instrumental improvement alone can account for. Even accounting for dust and resolution, the fraction of regular galaxies in the early universe implied by Webb's data substantially exceeds what any pre-launch model predicted. Something about how galaxies form ordered structure, or how robustly that structure survives the violent interactions of the early universe, does not match the standard hierarchical theory. Theorists are revising their models. Some argue that the disk-forming process is more efficient than assumed, settling gas into rotating structures on shorter time scales. Others argue that feedback from early black holes regulates star formation in ways that maintain morphological regularity. Others still question whether the hierarchical paradigm itself requires fundamental revision at early times. Webb has compounded the puzzle with discoveries at the extreme end of the observable universe. Galaxy GNZ1 observed as it existed only 430 million years after the Big Bang, at a redshift of approximately 10.6, contains a supermassive black hole at its center. Webb's spectroscopic observations confirmed this through the detection of characteristic emission lines from hot gas orbiting and accreting onto the black hole. The black hole's mass is estimated at several million solar masses. Not large by the standards of mature galaxies, but enormous given the age of the host galaxy. Under standard models of black hole growth, reaching this mass from a stellar mass seed in fewer than 500 million years requires sustained near-maximum accretion. A more extreme case is the galaxy JADE SGAZ 14-0, confirmed in 2024 as one of the most distant spectroscopically observed galaxies, existing only 290 million years after the Big Bang. Its spectrum contains oxygen, an element that cannot be produced in the Big Bang and that requires stellar nucleosynthesis. The presence of oxygen in a galaxy 300 million years old means that at least one generation of massive stars was born, lived for a few million years, and died in supernovae that enriched the surrounding gas, all before the observation epoch. This is not impossible. Massive stars live only a few million years, but it requires that star formation began essentially as soon as the first dark matter halos collapsed, with essentially no delay. Galaxy GS9 to Zephyr 9, at a redshift of approximately 4.7, corresponding to an age of about 1 billion years for the universe, shows a predominantly old passive stellar population. Its star formation has already ceased. It is, in the language of astronomers, quenched, its gas supply has been consumed or expelled, and it is no longer making new stars. In the local universe, massive quenched ellipticals are common, the result of major mergers, feedback from supermassive black holes, and the gradual exhaustion of cold gas supplies. But seeing a massive quenched galaxy at 1 billion years after the Big Bang implies that this process, building a massive galaxy and then shutting off its star formation, completed in less than the first tenth of cosmic history. The theoretical question of what quenches star formation so efficiently at such early times, in an environment where cold gas should be abundantly available, is one of the outstanding unsolved problems in galaxy formation theory. Webb has made it more acute. Perhaps the most striking result from Webb's early operations is the sheer abundance of massive galaxies in the very early universe. Before Webb, models predicted that galaxies with masses exceeding 100 billion solar masses should not exist before a redshift of about 4, before the universe was roughly 1.5 billion years old. Webb found candidates for such massive galaxies at redshifts above 7 and 8, when the universe was less than 800 million years old, in numbers exceeding model predictions by factors of 10 to 100. Not all of these candidates have been spectroscopically confirmed, and some may have overestimated masses due to the presence of bright, active galactic nuclei contaminating the stellar light estimates. But the excess is robust enough across multiple independent teams and analyses to constitute a genuine challenge to the standard model. Either galaxy formation is more efficient than models assume, or some physics is operating in the early universe that models do not include. Or both. This precocious maturity at small scales is mirrored by anomalous structure at the largest ones. The cosmological principle, the assumption that the universe is statistically homogeneous and isotropic on sufficiently large scales, is one of the foundational axioms of modern cosmology. Without it, the field equations of general relativity become intractably complex, and the derivation of observational predictions requires approximations that have no clean physical justification. The principle does not require perfect uniformity everywhere. It requires that the average properties of the universe, sampled over large enough volumes, do not depend on where you are or which direction you look. Early work by Enasto and collaborators and by Peebles and collaborators in the 1970s established that the required scale was probably a few hundred megaparsecs above that scale. The universe appears statistically uniform. The theoretical ceiling on the size of coherent structures derived from the baryon acoustic scale and the growth of structure under gravity within lambda CDM is approximately 1.2 billion light years. Structures larger than this should not form as physically coherent, gravitationally organized objects within the age of the universe. This prediction can be tested by looking for organized structures, galaxy walls, rings, filaments on scales larger than this theoretical limit. In 2015, astronomer Lajos Balas and colleagues announced the discovery of a ring-like arrangement of 9 gamma-ray bursts spanning approximately 5 billion light-years across the sky, more than 4 times the theoretical limit on coherent structure. Gamma-ray bursts are among the most energetic events in the universe, cataclysmic explosions produced by the collapses of rapidly spinning massive stars into neutron stars or black holes, or by the mergers of cracked stellar remnants. Their afterglow emission spans the electromagnetic spectrum from radio to X-ray. Their peak gamma-ray luminosity is so extreme, temporarily outshining the entire rest of the universe, that they are visible at redshifts exceeding 9, corresponding to distances of tens of billions of light-years, because they occur in galaxies and because their host galaxy redshifts can be measured precisely. They serve as tracers of the large-scale distribution of galaxies across the observable universe. The ring discovered by Ballas and colleagues subtends 36 degrees of sky, more than 70 times the diameter of the full moon, and its 9 constituent gamma-ray bursts lie at similar redshifts, corresponding to distances of roughly 7 billion light-years, within a narrow spread, suggesting they are all at approximately the same cosmic distance. A concentration of 9 gamma-ray bursts arranged in a ring by chance, given the known distribution of burst positions across the sky, has only a 1 in 20,000 probability. Whether this ring represents a true physical structure, a vast shell of galaxy filaments perhaps, or a ring of overdensity produced by a massive ancient explosion during the earliest epochs of the universe, or a statistical projection artifact that future data will dissolve, remains contested. But it joins a list of structures whose sizes challenge the cosmological principle. The Sloan Great Wall, discovered in 2003 from data in the Sloan Digital Sky Survey, extends more than 1.37 billion light-years in its longest dimension, already beyond the theoretical limit for a coherent structure. It is a complex of galaxy superclusters, including the Coma supercluster and several adjacent structures, arranged in a roughly sheet-like pattern at a distance of approximately 1 billion light-years. Its discovery, announced by Gott and colleagues using data from the SDSS main galaxy sample, temporarily made it the largest known structure in the universe. The CF82 Great Wall, discovered in 1989 by Geller and Hukra from the Harvard Redshift Survey, extends roughly 500 million light-years, smaller than the theoretical limit, but at the time an object without obvious explanation in standard models. It includes the Coma cluster and the Perseus-Species supercluster as its most prominent components, arranged in a sheet stretching across a large fraction of the northern sky. The Hercules Corona Borealis Great Wall dwarfs both of these, identified in 2014 by Ballas, Horvat and Bagoli from the distribution of gamma-ray bursts across the sky. And confirmed by subsequent analysis, it extends more than 10 billion light-years in its longest dimension, approximately 10% of the diameter of the entire observable universe, and roughly 8 times the theoretical maximum for a coherent structure. It is not a galaxy wall in the conventional sense. It has not been mapped through galaxy redshift surveys at that distance, because no current survey reaches far enough to map the galaxy distribution on those scales. It is instead inferred from the spatial clustering of gamma-ray bursts, under the assumption that bursts trace their host galaxies, and that their host galaxies trace the underlying mass distribution. This assumption may not hold perfectly. The relationship between gamma-ray burst rates and galaxy properties at high redshift is imperfectly understood. But the spatial clustering is statistically significant and has been confirmed by multiple independent analyses. If the Hercules Corona Borealis Great Wall represents a genuine physical structure, it violates the cosmological principle by a large margin. Each of these structures, the ring, the Sloan Great Wall, the Hercules Corona Borealis Wall, challenges the prediction that the universe should be statistically uniform on scales above about 1.2 billion light-years. Together, they suggest either that the theoretical limit is wrong, which would require modifying the standard model, or that the structures are statistical fluctuations, which requires very large fluctuations, or that the methods used to identify them have systematic biases that inflate apparent structure. All three possibilities are actively debated. The debate has sharpened as surveys have improved, and no consensus resolution has been reached. Meanwhile, in the southern sky, in the direction of the constellation Eridanus, there is a region that has troubled cosmologists for 2 decades. The cosmic microwave background, the faint afterglow of the Big Bang, filling the universe in every direction with radiation cooled to a temperature of 2.725 Kelvin, varying across the sky by only a few hundred thousandths of a degree, contains one conspicuous anomaly. A patch of sky roughly 2 billion light-years across radiates at a temperature approximately 70 microkelvin below the surrounding background. This is the cold spot, sometimes called the Eridanus supervoid. To grasp what 70 microkelvin represents, the average fluctuation in the cosmic microwave background is roughly 18 microkelvin. The cold spot is nearly 4 times larger than background variance. It covers a region of sky several degrees in diameter, visible as a distinct feature even in low-resolution maps of the microwave background. It was detected in WMAP data shortly after that satellite's first release in 2003, confirmed by the Planck satellite with better angular resolution, and has survived every methodological challenge directed at it. It is real. The integrated Sachs-Wolf effect, the leading physical explanation, works as follows. A photon entering a gravitational potential well in a matter-dominated universe gains kinetic energy descending into the well, then loses exactly the same energy climbing out the other side. In a universe dominated by dark energy, potential wells become shallower over time as the accelerating expansion dilutes the matter density. A photon entering a void when the void is shallow and exiting when the void has grown deeper leaves the void with less energy than it entered. The net result, integrated along the photon's path through the void, is a slight cooling, a temperature decrement detectable as a cold spot in the microwave background map. The magnitude of the effect scales with the depth and physical extent of the void. A supervoid 1 billion light-years in diameter, with a density contrast of 20 to 30% below the cosmic average, would produce a temperature decrement on the order of a few tenths of microkelvin. This is broadly consistent with the observed cold spot, though detailed models have found it difficult to simultaneously match the size, depth, and temperature profile of the feature with a plausible void distribution. 3-dimensional maps of the cold spot region, compiled from photometric redshift surveys, including the Dark Energy Survey and Pan-STARRS, have confirmed the presence of an under-death region in that direction. Surveys of the galaxy number density in and around the cold spot have found a systematic deficit of galaxies, consistent with a supervoid spanning several hundred megaparsecs. But whether this observed underdensity is large enough and deep enough to account for the full temperature decrement through the Sachs-Wolf mechanism remains debated. Some analyses find the effect from the observed void sufficient, others find a residual temperature anomaly that the void alone cannot explain, leaving open the possibility that some additional mechanism is also contributing. Other explanations have been proposed over the years. A cosmic texture, a topological defect in a symmetry-breaking quantum field left over from a phase transition in the early universe would produce a localized deformation in the density field with a characteristic radial profile, a cold core surrounded by a warm ring, precisely matching the observed structure of the cold spot. Textures are permitted by certain extensions of the standard model of particle physics, though whether any such extension is correct is unknown. A bubble collision in the multiverse, the imprint on our cosmic microwave background from an early universe collision with an adjacent bubble universe, would also produce a circular anomaly whose temperature profile depends on the geometry and energy of the collision. The cold spot's roughly circular shape, its anomalously cold interior, and its location in a region of genuine underdensity are at least qualitatively consistent with this interpretation, though the mathematics of such collisions is sufficiently complex that precise predictions are difficult to make and test. Whether either explanation is correct, or whether the cold spot is simply an unusual but not impossible fluctuation in a statistically rare region of the cosmic microwave background, remains an open question. It sits there in the southern sky, in the direction of Eridanus, a conspicuous silence in the otherwise nearly uniform afterglow of creation. Cold where the universe is not supposed to be so cold, empty where the universe is not supposed to be so empty, at all of these scales. Observation outpaces explanation. The universe contains structure that theory struggles to accommodate. Voids larger than they should be, walls longer than they should be, galaxies more organized than they should be, harboring black holes more massive than they should be, seeded with heavy elements earlier than they should be. And we sit at the center of the largest void currently known to science, peering outward into a cosmos that looks on the largest scales like a three-dimensional foam galaxy filaments surrounding spherical underdesk bubbles, each bubble bordered by sheets and threads of compressed matter. The entire structure shifting imperceptibly over billions of years as voids grow and filaments drain. The tools we use to map this structure are themselves remarkable. The Dark Energy Spectroscopic Instrument, or DESI, mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, is the largest redshift survey ever undertaken. Its focal plane is equipped with 5,000 robotic fiber positioners, each capable of repositioning to point at a new galaxy target in a few seconds. In a single night of operations, DESI can measure the spectra and distances of more than 100,000 galaxies, building a three-dimensional map of galaxy positions and peculiar velocities at a rate that no previous survey could approach. Its primary scientific goals are to measure the baryon acoustic oscillation scale across a wide range of cosmic epochs, from the nearby universe to redshifts above 2, and thereby trace the expansion history of the universe with sufficient precision to distinguish between different dark energy models. The Vera Rubin Observatory, being commissioned on Cerro Pachon in Chile, will image the entire visible southern sky every 3 nights for 10 years using an 8.4-meter primary mirror and a 3.2 gigapixel camera, the largest digital camera ever built. Each image will cover a field of view 10 times the area of the full moon. The resulting 10-year dataset, the Legacy Survey of Space and Time, will contain photometry for about 20 billion galaxies, measured on multiple occasions. This cadence makes it a transient survey as well as a structural one. It will detect tens of thousands of supernovae, hundreds of thousands of gravitational lens events, millions of asteroid positions, and countless other time-variable phenomena. The structural survey component will produce weak gravitational lensing maps. Statistical measurements of the distortion of background galaxy shapes by the mass of intervening structure that will map the dark matter distribution in 3 dimensions across most of the observable universe. The Euclid Space Telescope, launched in July 2023, is conducting a deep photometric and spectroscopic survey of the extragalactic sky from orbit, targeting more than 1 billion galaxies over 6 years. Its primary cosmological probes are weak. Gravitational lensing and baryon acoustic oscillations measured simultaneously across a large homogeneous dataset. Euclid's advantage over ground-based surveys is the stability and resolution of space. Without the blurring effect of the atmosphere, it can measure the subtle shape distortions of background galaxies caused by weak lensing with much greater statistical precision. Its combination with DESI and Rubin data will provide cosmological constraints that no single survey could achieve alone. Machine learning has become an indispensable tool in the analysis of these massive datasets. Modern redshift surveys produce data at rates that no team of human astronomers could analyze by eye. A single night of these eye operations yields several 100,000 galaxy spectra. A single night of Rubin observations will produce roughly 15 terabytes of raw imaging data. machine learning algorithms handle source detection, spectral classification, redshift estimation, morphological classification, anomaly detection, and cosmological parameter inference at each stage of the analysis pipeline. The algorithms are trained on simulated data, simulated galaxy images, simulated spectra, simulated peculiar velocity fields, and then applied to real observations with careful validation to ensure that the training distribution matches the observed distribution. The application of neural networks to cosmological inference has produced results that would have seemed implausible a decade ago. The CAMELS project, Cosmology and Astrophysics with Machine Learning Simulations, generated over 4,000 simulated universes, each with different values of the matter density, the amplitude of density fluctuations, and the parameters governing star formation and supernova feedback, then trained neural networks to infer these parameters from the simulated galaxy populations. In one remarkable demonstration, a network trained on simulated galaxy properties was able to estimate the cosmological matter content of a simulated universe from the properties of a single galaxy within it, the cosmological equivalent of inferring the composition of an entire desert from a single grain of sand. The method works because the universe encodes its own history in every structure it produces. Every galaxy's observable properties, its mass, its morphology, its star formation rate, its gas fraction, its black hole mass, its stellar age distribution reflect the cosmological environment in which it formed and evolved. The same hierarchical logic that enables machine learning to function is the logic of the universe itself. Elementary particles form atoms. Atoms form molecules. Molecules form dust grains and gas clouds. Gas clouds collapse into stars. Stars forge heavy elements through nuclear fusion and disperse them in supernova explosions. The debris collects into new star systems and planets, into chemistry, into biology. Stars cluster into galaxies, galaxies cluster into groups, groups cluster into superclusters. Superclusters thread along filaments, filaments border voids. At each level, the structure of the smaller scale reflects and encodes the structure of the larger. A neural network trained on galaxy properties does not need to approximate an arbitrary function of unlimited complexity. It only needs to approximate the small subset of functions that the physics of our universe actually generates. And those functions share a set of special properties: symmetry under rotation and translation, locality of physical interactions, hierarchical structure arising from physical processes that operate similarly at different scales that make them far easier to approximate than the general case. The universe is comprehensible. Not because human minds are capable of understanding anything, but because the laws governing the universe are, in a mathematically precise sense, simple. They could have been arbitrarily complex. They are not. The Milky Way orbits the center of the galaxy at roughly 220 kilometers per second, completing one full revolution every 250 million years, a period sometimes called a galactic year. In that motion, we ride through the Orion Arm, a minor spore of spiral structure branching off the inner edge of the Sagittarius Arm, populated by the Sun and several thousand other stellar systems, dense molecular clouds and young star-forming regions, including the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, and dozens of other active sites of stellar birth. The Sun joined this arm approximately 5 billion years ago, condensing from a molecular cloud whose identity is now lost to galactic mixing, though isotopic anomalies in meteorites hint that a nearby supernova may have triggered the cloud's collapse and contributed enriched material to the forming solar system. The Orion Arm itself is embedded within the local bubble, a region of hot, rarefied plasma roughly 300 light-years across. Its interior swept nearly clean of interstellar dust and gas by a sequence of supernova explosions over the past 14 million years. The origin of the local bubble was traced by ESA's Gaia Space Observatory, which measured the positions, parallaxes, and proper motions of nearly 2 billion stars in the Milky Way with extraordinary precision. By running the measured stellar motions backward in time, researchers identified the source of the bubble, the Scorpius-Centaurus OB association, a loose cluster of massive hot stars formed about 15 million years ago, now in the process of gradually dispersing as its members age and drift apart. As the most massive stars of this association exploded in sequence, each supernova sent a shock wave of hot plasma, expanding into the surrounding interstellar medium, adding energy and momentum to the bubble that their predecessors had begun to carve. The solar system entered the local bubble's interior about 5 million years ago, well after the bubble was established, as the galactic disk rotation carried our neighborhood into the region excavated by the Scorpius-Centaurus supernovae. The Gaia data also revealed that the local bubble has not been passive. It is currently expanding its hot interior, pushing outward against the surrounding cold interstellar medium. The dense shells of gas and dust accumulated at its boundaries, swept up by the expanding shock waves from the ancient supernovae, are the sites of active star formation today. The Ophiuchus molecular cloud complex, the Taurus Auriga cloud, the Perseus molecular cloud, the Orion molecular cloud, the most active nearby stellar nurseries within a few hundred light years of the Sun, all lie approximately on the surface of the local bubble, compressed into star-forming density by the bubble's expanding walls. In a real sense, the stellar nurseries that are currently producing the Sun's nearest future neighbors are the direct consequence of the supernovae that cleared the local bubble millions of years ago. The local interstellar environment is an ecosystem. The deaths of massive stars create the conditions for the births of new ones, and the Sun orbits through successive generations of this cycle. Within the local bubble drift several interstellar clouds, dense knots of neutral hydrogen and dust embedded in the surrounding hot plasma. The Sun is currently passing through one of them, the local interstellar cloud, sometimes called the local fluff, a wisp of warm gas roughly 30 light years across, moving relative to the Sun at about 26 kilometers per second in the direction of the constellation Ophiuchus. Despite the term, it contains very little material by terrestrial standards, a few thousand hydrogen atoms per cubic meter, compared to the 10 to the 25th atoms per cubic meter that fill the air we breathe. But it is enough to interact with the outer boundary of the heliosphere. The boundary of the solar system, the heliosphere, is the bubble of solar wind that the Sun inflates against the surrounding interstellar medium. The solar wind is a continuous stream of charged particles, protons, electrons, alpha particles, expelled from the Sun's corona at speeds of several hundred to several thousand kilometers per second. It flows outward in all directions, gradually decelerating as it collides with the interstellar medium, eventually terminating at the heliopause, the surface where the solar wind pressure equals the pressure of the interstellar plasma. The solar system's position in the Milky Way, in the Orion Arm, roughly 26,000 light-years from the galactic center, in the midplane of the disk, is itself a product of the cosmic web's hierarchy. The Milky Way is a barred spiral galaxy, a disk of stars, gas and dust, interrupted by a central bar of older, redder stars, from whose ends spiral arms unwind. The bar is roughly 27,000 light-years in length. The spiral arms are density waves, regions of slightly enhanced gravitational potential that travel through the disk, at a speed different from the speed at which individual stars orbit, sweeping through the stellar population and compressing gas as they pass. Molecular clouds compressed by the passage of a spiral arm collapse into stars, producing the bright young blue stars and star-forming regions that outline the arms in galaxy images. The Sun is currently between the major Perseus arm and the Sagittarius arm. in the minor spur called the Orion Arm, where the arm is currently producing the Orion Nebula and other nearby star-forming regions. At the very center of the galaxy, within a few light years of the dynamical center, orbits the supermassive black hole Sagittarius A star, 4 million solar masses compressed into a region smaller than our solar system. Precise measurements of the stellar orbits around it over more than 2 decades, pioneered by Reinhard Genzel's team and Andrea Ghe's team. Work that earned both the Nobel Prize in Physics in 2020 provided the most direct evidence for the existence of a supermassive black hole and led to the measurement of its mass with extraordinary precision. The Event Horizon Telescope, a global network of radio dishes linked by atomic clocks to form an Earth-sized virtual telescope, imaged the shadow of Sagittarius A star directly in 2022, producing a photographic image of the black hole's event horizon silhouette against the surrounding glowing plasma. The Milky Way's central black hole is currently quiet, but the Fermi bubbles, 2 enormous lobes of gamma-ray emission extending roughly 25,000 light-years above and below the galactic plane, may be the relic of a powerful outflow event that occurred several million years ago, when Sagittarius A star was accreting at a much higher rate. The feedback between black holes and their host galaxies has shaped the Milky Way as surely as it has shaped more dramatically active galaxies at higher redshifts. The dwarf galaxies of the local group, the small satellite systems orbiting the Milky Way and Andromeda, are among the most dark matter-dominated objects in the universe. Their visible stars contribute only a few % of their total mass. The rest is dark matter. This makes them valuable laboratories for dark matter physics. Their internal dynamics are almost entirely determined by their dark matter content, uncontaminated by the baryonic complexity that makes larger galaxies difficult to model. The Fermi Gamma-Ray Space Telescope has searched for a dark matter annihilation signal in dwarf galaxies without finding it, placing the most stringent constraints on WIMP annihilation cross-sections available from any single class of observation. The dwarfs are silent in gamma rays. But their silence constrains dark matter as surely as a detection would. The relationship between voids and the populations of galaxies they contain is a window into how environment shapes the evolution of matter over cosmic time. A galaxy forming in the interior of the Boet's void evolved in near total isolation, governed by its own internal dynamics, never disturbed by a major merger partner, never stripped of its gas by a neighboring halo's gravity, never heated by a cluster's X-ray gas. A galaxy forming in the Coma cluster forms in an environment of constant disruption, repeated close encounters, ram pressure stripping, tidal harassment, submergence in hot plasma. Both galaxies obey the same physical laws. Both started from similar primordial material. The difference in their evolutionary histories encoded in their current properties is entirely the product of their environment. The cosmic web is not merely the background against which galaxy evolution occurs. It is a principal driver of that evolution. The Voyager 1 spacecraft, launched in September 1977 and now approximately 23 billion kilometers from the Sun, crossed the heliopause in August 2012 at a heliocentric distance of approximately 121 astronomical units. It was the first human-made object to enter interstellar space. Its instruments, designed in the 1970s, when the expected lifetime of the mission was only a few years, recorded the properties of the plasma and the magnetic field in the immediate interstellar medium directly, providing the first in situ measurements ever made of the local interstellar environment. The plasma Voyager 1 encountered upon crossing the heliopause was denser and hotter than expected, and the magnetic field was oriented at a larger angle to the ecliptic plane than most pre-crossing models predicted. Voyager 12 crossed the heliopause in November 2018 at a slightly different heliocentric distance and in a different direction, providing comparative measurements that revealed the heliopause is not a sphere, but a complex asymmetric boundary shaped by the ram pressure of our motion through the interstellar medium and by the orientation of the interstellar magnetic field. The upwind side of the heliosphere, the side facing our direction of motion through the local interstellar cloud, is compressed to smaller radii. The downwind side stretches into a long heliotail extending well beyond the current reach of any spacecraft. IBEX, the interstellar boundary explorer, orbits Earth and measures energetic neutral atoms streaming into the solar system from the heliopause, produced when solar wind ions exchange charge with neutral interstellar gas. Its maps of the energetic neutral atom sky revealed a ribbon of enhanced emission, a feature not predicted by any pre-launch model, whose origin is still debated, but is believed to reflect the interaction of the solar magnetic field with the interstellar magnetic field at the heliopause boundary. EMAP, the Interstellar Mapping and Acceleration Probe, launched in 2025, will measure these fluxes with greater precision and angular resolution, providing a more detailed picture of the heliospheric boundary and the local interstellar environment. The flux of galactic cosmic rays, high-energy charged particles produced in supernova shockwaves and other energetic sources throughout the galaxy. Reaching the inner solar system depends on the heliosphere's size and structure, which in turn depends on the density and magnetic field of the surrounding interstellar medium. When the Sun passes through denser interstellar clouds, the heliosphere may contract, allowing more cosmic rays to penetrate to the inner planets. Elevated cosmic ray fluxes affect atmospheric chemistry, producing additional ionization in the troposphere, potentially modifying cloud formation rates and climate, and increase the radiation dose experienced by any biology on planetary surfaces or spacecraft in transit. The Sun moves toward the constellation Hercules relative to local stars at about 20 kilometers per second, the solar apex, the point toward which the Sun's motion carries it through the local stellar neighborhood. The entire solar system tracks in the direction of Cygnus relative to the galactic center at 220 kilometers per second. The galaxy itself is drawn toward the great attractor in the direction of Centaurus, the combined gravitational pull of the Norma cluster and the vast Shapley supercluster at several hundred kilometers per second relative to the cosmic rest frame defined by the microwave background. And simultaneously, the local group of galaxies flows outward from the KBC void toward the denser walls of surrounding structure at roughly 200 kilometers per second. Every layer of this picture is in motion. Every motion is shaped by the gravitational influence of all surrounding matter, weighed and summed across the cosmic web. Nothing in this picture is stationary, nothing is isolated. The solar system is embedded in its cloud, the cloud in its bubble, the bubble in its galactic arm, the arm in its galaxy, the galaxy in its group, the group in its supercluster, the supercluster in its void. Layers of context, each one restructuring what the one inside it means. There is a boundary beyond which we cannot see. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, extends roughly 46 billion light years in all directions from Earth, not 13.8 billion, though that is the age of the universe in years. Space expanded during the time the light was traveling, carrying sources further than the naive calculation would suggest. The outermost light we detect, the cosmic microwave background, was emitted when the universe was only 380,000 years old, from a region of space that today sits approximately 46 billion light years away. The boundary of the observable universe is the particle horizon, the co-moving distance to the most remote region from which any signal could have reached us by the present day. traveling at the speed of light since the instant of the Big Bang. It is distinct from the Hubble sphere, the boundary inside which galaxies currently recede slower than the speed of light, which has a radius of roughly 14 billion light years. These two surfaces are frequently confused. The Hubble sphere is not a causal boundary. Galaxies well beyond it have had their light reach us because the expansion was slower in the past. The particle horizon is the true causal limit. No information from beyond it could have reached us by any physical means since the beginning of time. In the far future, both surfaces will grow as the universe ages, but the Hubble sphere grows more slowly than the particle horizon under an accelerating expansion, which has a paradoxical consequence. The set of galaxies whose light can ever reach us, the event horizon, is smaller than the set whose light has already reached us. The cosmological event horizon is distinct from both. It is the boundary of the region from which light emitted today can ever reach us. Given the accelerating expansion, any galaxy currently beyond the event horizon, located at roughly 16 billion light years, will never be able to send us a message that we can receive, no matter how long we wait. The accelerating expansion is carrying those galaxies away faster than the light they emit can overcome the growing distance. The set of galaxies we can communicate with is finite, fixed, and shrinking. Not in the sense that existing galaxies are disappearing from our sky, but in the sense that light from newly emitted events at those distances will never arrive. The universe is not merely large, it is actively becoming inaccessible. Eternal inflation, the theoretical framework in which our observable universe is one among an infinite number of independently inflated bubble universes, predicts that the laws of physics may differ between bubbles if the inflationary landscape of possible vacuum states is sufficiently large. String theory, which provides the most developed framework for a quantum theory of gravity, predicts a landscape of roughly 10 to the 500 possible vacuum states, each corresponding to a different set of physical constants, different particle masses, different force strengths, different cosmological constants. If even a small fraction of these states are realized in different bubble universes, the multiverse is not merely large, but radically diverse. Our universe, with its particular values of the fundamental constants, including the cosmological constant fine-tuned to within 1 part in 10 to the 120 of the Planck scale, would be understood not as a singular cosmic accident, but as one member of a vast ensemble in which every possible combination of constants is realized somewhere. Whether this framework constitutes science in the testable sense is a question that divides physicists. If no observation can in principle distinguish our universe from the ensemble, if the multiverse makes no prediction that can be falsified by any conceivable experiment, then it does not satisfy the conventional definition of a scientific theory. Some researchers argue that certain multiverse scenarios do make predictions, that the cosmological constant should have a value at the lower end of the range compatible with the development of complex structure, which is approximately what we observe, that the cold spot may be the imprint of a bubble collision, that the large angle anomalies in the cosmic microwave background polarization may reflect the influence of adjacent bubble universes on our inflationary initial conditions. Others argue that these predictions are too qualitative, too easily post-dicted, and too dependent on unknown measures over the multiverse ensemble to constitute meaningful falsifiable science. As dark energy continues to drive the acceleration of cosmic expansion, voids will not stay the same size. They will grow. The mechanism is straightforward. The accelerating expansion stretches the distances between all structures, preferentially depleting the already underdense interiors of voids, which lack the gravitational binding energy to resist the expansion. Filaments and clusters, gravitationally bound on small scales, will resist the expansion within their bound volumes. But on the scales of tens and hundreds of megaparsecs, where the gravitational binding is weaker than the repulsion of dark energy, the accelerating expansion will win. Voids will grow larger. Filaments will thin. The walls of the cosmic web will become more tenuous as galaxies on their surfaces flow inward toward dense clusters or outward into the growing voids, driven by the same gravitational dynamics that have always governed structure formation, now augmented by the dark energy background. Simulations of the far future of the cosmic web show a universe of increasing contrast, denser clusters surrounded by thinner filaments bordering larger, emptier voids. The foam becomes coarser, the threads thinner, the bubbles vaster. In the far future, tens of billions of years from now, the universe will look very different. Dark energy will have accelerated the expansion to the point that most galaxies beyond the local group are invisible. Their light redshifted to infinite wavelengths by the recession speed exceeding the speed of light, placing them permanently beyond the cosmological event horizon. The local group will have merged into a single massive object, the Milk-Dromeda galaxy, the product of the ongoing collision between the Milky Way and Andromeda that will reach its first close approach in approximately 4.5 billion years. Subsequent encounters will complete the merger within a few billion years of that. The resulting massive elliptical galaxy, its gas supply exhausted by the star formation triggered by the merger, its outer halo of red giant stars slowly fading, will orbit alone in an otherwise invisible universe. An astronomer in that era, with no knowledge of our current observations, would have no way to infer the existence of the Big Bang, the cosmic web, or the billions of other galaxies that once populated the observable universe. The information needed to reconstruct cosmological history will have been irretrievably carried beyond the event horizon. The cosmos will have amputated its own memory. This is worth pausing on. The questions we can ask and answer today about voids and filaments, about dark matter and dark energy, about the structure of the universe across billions of light years are only possible because we live at a particular moment in cosmic history. Early enough that the universe has not yet expanded to the point of informational isolation. Early enough that the light from distant galaxies has not yet stretched beyond detectability. Early enough that the cosmic microwave background is still visible as a coherent pattern, encoding the initial conditions of the universe. Astronomers who come a trillion years from now, if any exist, will be imprisoned by their horizon. They will look outward from a dark, isolated island of merged stars, with no way to know that the universe was once filled with light and structure and the observable signatures of its own origin. There is a subtle but important reason not to be surprised that we find ourselves inside a void. It is related to the same reasoning that explains why we should not be surprised to find ourselves on a planet with liquid water orbiting a stable star, in the disk of a quiescent galaxy rather than near the violent center. Dense cluster environments, the places where the most mass is concentrated, where the average density is highest, are in many ways hostile to complex chemistry and biology. Galaxy-galaxy interactions are frequent and disruptive, perturbing stellar orbits and destabilizing planetary systems. Intracluster gas is heated to temperatures of tens of millions of degrees by gravitational compression and energetic feedback from massive black holes, providing an intense radiation environment. Star formation in the dense cluster core is suppressed by gas stripping and heating, producing predominantly old, metal-rich stellar populations with little cold gas to form new solar systems. The outer edges of filaments and the walls of voids offer a quieter environment, more stable galaxies, less environmental harassment, longer timescales for planetary evolution and the development of complex chemistry. The Milky Way, sitting near the rim of Laniakea, in the interior of the KBC void, occupies precisely the kind of intermediate environment, not the dense cluster core, not the deepest void interior, where the conditions for long-lived stellar systems and the emergence of chemistry appear to be favorable. Whether this is a meaningful anthropic selection effect or merely a coincidence is a question that touches on the anthropic principle, the observation that our existence as observers constrains the conditions we can observe ourselves to occupy. The cosmological principle demands that no location is special in a statistical sense. The anthropic principle reminds us that observers are not randomly distributed across the universe. They can only exist where conditions for their existence are met. These two principles are not in conflict. They operate at different levels of description. The cosmological principle describes the statistical distribution of matter across the universe as a whole. The anthropic principle describes the subset of the universe accessible to observers. Our location in the largest known void, interpreted as anomalous from a purely statistical standpoint, might be less anomalous when the conditions required for our existence are taken into account. The voids are not merely the absence of matter. They are, perhaps, the precondition for the kind of matter that asks questions. The neutrino sector offers another window into the relationship between the large-scale structure of the universe and the fundamental particles from which it is built. The three known species of neutrinos, electron, muon, and tau, have small but non-zero masses established by the observation of neutrino oscillation, the phenomenon in which neutrinos spontaneously change from one flavor to another as they propagate. Oscillation is only possible if the mass eigenstates of the neutrino differ from the flavor eigenstates, and if at least two of the mass eigenstates have different masses. The mass differences between neutrino species are known from oscillation experiments. The absolute mass scale is not. Only the sum of the three neutrino masses can be constrained cosmologically through their effect on the growth of structure. Neutrinos are produced in vast numbers in the Big Bang, the cosmic neutrino background, analogous to the cosmic microwave background, permeates the universe at a density comparable to the microwave background photons, roughly 336 neutrinos per cubic centimeter of space, everywhere always. They travel at nearly the speed of light even in the current universe, because their masses are extraordinarily small. Because they move so fast, they tend to free stream out of overdense regions rather than accumulating in them. They carry energy from denser regions to underdense ones, smoothing out density variations on scales smaller than their free streaming lengths. This suppresses the growth of structure on small scales. The more massive the neutrinos, the larger their free streaming lengths, and the more strongly they suppress small-scale structure. Cosmological measurements of the small-scale matter power spectrum, the amplitude of density variations as a function of spatial scale, therefore constrain the neutrino mass sum. The current best cosmological upper limit, combining data from the Planck satellite Borean acoustic oscillation surveys and weak gravitational lensing, is approximately 0.12 electron volts for the sum of all three masses. This upper limit is extraordinarily tight. A single electron, the lightest charged lepton, outweighs all three neutrino species combined by a factor of roughly 4 million. And yet, those tiny masses leave measurable imprints on the largest structures in the observable universe. Voids in a universe with massive neutrinos are slightly larger and slightly emptier than voids in a universe with massless neutrinos, because the free streaming of neutrinos out of underdense regions adds to the evacuation rate. Filaments are slightly thinner, galaxy clusters are slightly less massive. The differences are at the level of a few percent, small enough to be invisible in any single measurement, but detectable in the statistics of millions of galaxies. Future surveys, particularly DESI, Euclid, and the CMB-S4 experiment, are expected to achieve sensitivity to the neutrino mass sum well below 0.1 electron volts, comparable to the minimum value required by oscillation measurements. If the neutrino mass sum is at or near its minimum, the so-called normal hierarchy scenario, in which the lightest neutrino is nearly massless, these surveys may detect the neutrino mass directly through its effect on galaxy clustering. If the mass sum falls below the minimum required by oscillation experiments, it would indicate new physics beyond the standard model of particle physics. Either way, the large-scale structure of the universe encodes information about the fundamental particles that make up its matter content at a precision that no laboratory experiment can yet match. Fast radio bursts represent another emerging probe of voids and the intergalactic medium. These are brief, intense pulses of radio emission lasting a few milliseconds or less, originating from cosmological distances, billions of light years away, from sources whose nature was debated for years after their discovery in 2007, and is now largely identified with magnetars, rapidly rotating neutron stars with extraordinarily powerful magnetic fields. When a fast radio burst travels through intergalactic space, its radio waves are dispersed by the free electrons in the intergalactic medium. Lower frequencies arrive slightly later than higher frequencies, by an amount proportional to the total column density of electrons along the line of sight, the dispersion measure. This dispersion measure is a direct measurement of the total amount of ionized gas that the burst traversed, combined with the source redshift, measured through the identification of the host galaxy. The dispersion measure provides a constraint on the average electron density of the intergalactic medium, and through it on the total baryon content of the universe along that line of sight. Fast radio bursts that pass through voids accumulate less dispersion than bursts that pass through filaments, because voids contain less ionized gas. Statistical analysis of the dispersion measures of large samples of bursts, as a function of their redshifts and their angular positions on the sky, can therefore map the distribution of ionized gas across the cosmic web, independently of galaxy surveys. This technique has been used to confirm that voids are genuinely underdense in baryons as well as in galaxies, and to measure the baryon content of the warm-hot intergalactic medium with increasing precision. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, detects hundreds of fast radio bursts per year and is building the statistical sample needed for this kind of cosmological measurement. The future square kilometer array will detect thousands per day, providing a map of the intergalactic medium at a level of detail comparable to what galaxy surveys provide for the stellar component of the cosmic web. Gravitational waves, ripples in the curvature of spacetime produced by the acceleration of massive compact objects, provide yet another independent probe of the universe's expansion history and large-scale structure. The merger of two neutron stars or two black holes produces gravitational waves whose amplitude depends on the masses of the merging objects and their distance from the observer, because gravitational wave sources are self-calibrating. Their intrinsic luminosity can be calculated from the observed waveform without any external calibration. They serve as what cosmologists call standard sirens, analogous to standard candles in optical astronomy. The Hubble constant can be measured from a single gravitational wave event whose host galaxy is identified by combining the gravitational wave distance with the host galaxy's redshift. The first such measurement was made in 2017, when the neutron star merger GW170817, detected by LIGO and Virgo and accompanied by an electromagnetic afterglow that allowed the host galaxy to be identified, provided a Hubble constant measurement of roughly 70 kilometers per second per megaparsec with an uncertainty of 14%. Future observations, particularly from the planned LISA space-based gravitational wave detector and the next generation Einstein telescope and Cosmic Explorer ground-based observatories, will accumulate hundreds or thousands of standard siren measurements, providing a Hubble constant determination independent of both the distance ladder and the microwave background, with the potential to definitively resolve or confirm the Hubble tension. The lambda CDM model, cold dark matter, plus a cosmological constant, tested against thousands of independent observations across many decades, is the most precisely confirmed physical theory ever applied to the universe as a whole. It predicted the baryon acoustic oscillation scale from first principles before it was observed. It predicted the detailed angular power spectrum of the cosmic microwave background, the precise pattern of temperature and polarization fluctuations across the sky. And the Planck satellite confirmed this prediction to sub-percent accuracy across multiple angular scales. It predicted the large-scale matter distribution that galaxy surveys subsequently confirmed. It predicts the abundance and properties of galaxy clusters, the weak gravitational lensing signal, the integrated Sachs-Wolf effect, the primordial helium abundance, and dozens of other observational quantities. And it matches them all to high precision, and yet it fails or appears to fail at precisely the level of detail that modern instruments have achieved. The anomalies are not large, they are subtle, but they are persistent, and they are accumulating the Hubble tension, the sigma-8 tension in matter clustering. The KBC void anomalously large by the standards of the Standard Model. Webb's galaxies more mature than they should be. The cold spot colder than it should be, the Hercules Corona Borealis Great Wall larger than it should be. Each of these is a thread hanging loose from the fabric of our understanding. Each of them tugs. The question is whether they are all pulling at the same loose thread, some single modification to the Standard Model that, once identified, will accommodate all the anomalies simultaneously. Or whether they are different threads, each pointing to a different limitation of the model, requiring different corrections in different regimes. This is the central scientific question of contemporary cosmology, not whether the Standard Model is approximately correct, it clearly is, but whether it is the final word or the beginning of a deeper understanding. The future of the cosmic web, projected forward in time beyond the current epoch, unfold under the combined influence of gravity and dark energy in a way that is predictable in broad outline but rich in detail. On the scales of individual galaxy clusters, gravity wins. The local group will eventually merge with the Virgo cluster and other nearby structures, drawn together into a single massive system over timescales of tens of billions of years. Simulations of this process show a sequence of increasingly violent mergers. The Milky Way and Andromeda merge in roughly 5 billion years, producing the Milk-Andromeda galaxy. This object subsequently merges with other members of the local group. The merged local group eventually falls toward the Virgo cluster and merges with it. All of this occurs while the accelerating expansion of the universe carries more distant structures beyond communication and beyond reach. On scales larger than the bound local group, dark energy dominates the dynamics. The accelerating expansion stretches distances between unbound structures faster than gravity can counteract. Galaxy clusters beyond the local group will recede from us at increasing speeds, their light increasingly redshifted, their apparent brightness fading. In roughly 100 billion years, roughly 7 times the current age of the universe, all galaxies currently visible beyond the local group will have crossed the cosmological event horizon. Their light redshifted to wavelengths too long for any conceivable detector, their existence knowable only from the historical record of observations made in our current epoch. The cosmic web will continue to exist in the sense that the matter in filaments and clusters will continue to cluster and evolve, but we will no longer be able to observe it. The universe, as experienced by any future observer in the local group remnant, will be a dark, apparently static, isolated island of stars. On even longer time scales, the stars themselves will fade. The most massive stars live only a few million years. They are already long gone. Stars like the Sun live 10 billion years, comparable to the current age of the universe. The least massive red dwarf stars, which burn hydrogen so frugally that they can sustain fusion for trillions of years, will be the last lights to go out. In roughly 10 trillion years, the last red dwarf will exhaust its fuel and fade to a cold, dark brown dwarf, a degenerate sphere of carbon and oxygen, no longer capable of nuclear burning. White dwarfs, the remnants of intermediate mass stars, will slowly cool over quadrillions of years, eventually becoming cold, dark black dwarfs. Neutron stars, the remnants of the most massive stars that do not produce black holes, will cool and fade similarly. Black holes, through Hawking radiation, the slow quantum process by which pairs of virtual particles produced near the event horizon result in a net energy loss from the black hole, will eventually evaporate, the largest ones taking times that dwarf the current age of the universe by inconceivable factors. After the last black hole evaporates, in a time roughly equal to 10 to the power of 100 years, a number so large that it exceeds the number of atoms in the observable universe by a vast margin. The universe will contain only the residual radiation from Hawking evaporation, perhaps some relic stable particles, and the vacuum energy of space. This state, cold, dark, diffuse, essentially featureless, is the thermal death of the universe. Maximum entropy, minimum useful energy, no gradients across which work could be done or information processed. It is the ultimate endpoint of the second law of thermodynamics applied to a closed system extended to cosmic scales. Whether it is truly the final state depends on what dark energy actually is, if it is truly a cosmological constant or if it changes over time. Some models of dark energy allow for a scenario called the Big Rip, in which dark energy grows stronger over time, eventually overcoming not just the gravity between galaxy clusters, but the gravity within galaxies, then between stars, then within solar systems, then between atoms and nuclei, shredding all bound structures in a finite time. Other models allow for a big crunch, in which dark energy eventually reverses sign, converting from repulsive to attractive, causing the expansion to reverse and the universe to collapse back to a singularity. The observational evidence currently favors neither the Big Rip nor the Big Crunch. The dark energy equation of state appears consistent with a pure cosmological constant, though the uncertainties allow for slow evolution that does not obviously lead to either extreme. The fate of the universe remains, in this precise technical sense, an open question. What is certain is that the structure we observe today, the cosmic web of filaments, clusters, and voids, is a temporary phenomenon in the life of the universe. It assembled over billions of years from the primordial fluctuations of inflation. It will persist for billions more, slowly evolving, slowly growing, slowly draining as the voids empty and the clusters grow denser. Eventually, the accelerating expansion will begin to isolate the individual bound structures from one another, and the web will become invisible to any observer within it. The era of large-scale structure, the era we currently inhabit, is a brief window in cosmic history, bounded on one side by the reionization epoch that lit the first galaxies, and on the other by the isolation that dark energy will eventually impose. We live in that window. The fact that we can observe the cosmic web at all, that we live in an epoch when the universe has had time to develop complex structure, but not yet enough time to be torn apart by dark energy, is not a coincidence from the anthropic perspective. Observers like us could not exist before the first stars formed and may not exist after the stars fade. The window is the necessary condition for our existence. And from within the window, we look outward at the structure of the web and attempt to understand from within the shape of something that no observer can ever see from outside. What we do know is this: within the sphere we can observe, matter is not distributed randomly. It is organized into a web of extraordinary complexity, voids bordered by filaments, filaments meeting at nodes where the most massive galaxy clusters reside, the whole structure evolving slowly as dark energy continues to accelerate the expansion of space. Every photon we have ever received from beyond the Milky Way crossed some portion of this web. Every redshift we have measured was shaped by the intervening structure. Every map we have drawn is a map not only of where galaxies are, but of where matter chose to go, guided by forces we can describe mathematically but have not fully understood. The map is incomplete, it always will be. The incompleteness itself is information. The boundary of the observable universe, the surface of last scattering where the cosmic microwave background was emitted, is not merely a technical limitation. It is a physical limit imposed by the finite speed of light and the finite age of the universe. But it is not fixed. As time passes, light from regions currently beyond our particle horizon will eventually reach us, not because those regions have moved closer, but because we have moved further into the future, and light emitted long ago from those regions has had more time to travel. Every second, the observable universe grows by 1 light second of radius. The rate of growth is tiny compared to the scale, but it is real over billions of years. The additional volume that enters the observable sphere may contain structures and phenomena not represented in the current sample. Patience extended to cosmic scales reveals new territory. The universe also reveals itself to us not only in light. The recent opening of the gravitational wave window, initiated by LIGO's detection of GW 15-914 in 2015, the merger of 2 black holes 36 times the mass of the Sun at a distance of 1.3 billion light-years, has provided a completely independent channel of astronomical observation, uncorrupted by the electromagnetic biases of traditional astronomy. Gravitational waves pass through matter unimpeded, unabsorbed, unscattered. They carry information from environments, the interiors of merging compact objects, the vicinity of event horizons that are forever inaccessible to electromagnetic observation. They measure distances geometrically without relying on the empirical calibrations that underpin the cosmic distance ladder. And they will, as the sensitivity of detectors improves, provide cosmological measurements of the Hubble constant, of the distribution of binary compact objects across cosmic history, of the merger rate of massive black holes in galaxy centers, that complement and cross-check everything we know from electromagnetic surveys. The question of what observational strategy is most likely to resolve the current tensions in cosmology, Hubble tension, sigma-8 tension, the anomalous sizes of voids and walls, has no single agreed answer. But several broad approaches are clear. The first is to improve the precision and systematics control of existing measurements. The Nancy Grace Roman Space Telescope, a wide-field infrared telescope with a field of view 100 times larger than Hubble's wide-field camera, will measure Cepheid distances and Type Ia supernova distances with greatly improved statistics and systematics control, either confirming the high Hubble constant value at higher confidence or revealing a systematic error that has affected all previous measurements. The CMB-S4 experiment, a next-generation ground-based microwave background observatory deploying hundreds of thousands of detector elements at the South Pole and in Chile, will measure the CMB temperature and polarization with so much sensitivity that nearly every potentially useful bit of information in the temperature signal will have been extracted, while the polarization will provide new probes, including the optical depth to reionization and the gravitational lensing potential. CMB-S4 is expected to achieve sensitivity to the sum of neutrino masses, comparable to the minimum mass implied by oscillation experiments, providing either a detection or a definitive model-independent constraint. The second approach is to develop new independent probes. Gravitational wave standard sirens, the Hubble constant measurements from compact binary mergers discussed earlier, are perhaps the most promising entirely independent method. With hundreds of events in the LIGO-Virgo-Kagra data over the next decade, the statistical uncertainty on the gravitational wave Hubble constant will drop to a few percent. LISA, the Laser Interferometer Space Antenna, will detect gravitational waves from massive black hole mergers at cosmological distances, events visible throughout the observable universe and from extreme mass ratio in spirals in which stellar mass compact objects spiral into massive black holes, producing waveforms so rich in information that the source distance can be measured with exquisite precision. Time delay cosmography. Using the different arrival times of multiple images of the same quasar, produced by strong lensing by an intervening galaxy, to measure the Hubble constant is being pursued by the TDS-Cosmo collaboration and others. Each method brings its own systematic errors, but their combination provides cross-checks that no single method alone can offer. The third approach is theoretical, to construct models that can simultaneously accommodate all the observations and to sharpen the predictions of those models until they can be falsified by current data. Early dark energy models, interacting dark matter dark energy models, self-interacting dark matter models, modified gravity theories, each of these makes specific predictions beyond the Hubble constant and sigma 8, predictions that future surveys will be able to test. If a model resolves the Hubble tension but simultaneously predicts a void size distribution or a galaxy morphology distribution or a neutrino mass sum or a gravitational wave event rate that is inconsistent with observation, the model can be ruled out. The process of theory proposal and observational falsification, the basic engine of scientific progress, continues to operate at cosmological scales, slowed by the enormous investment required to build each new instrument, but inexorable in its long-term tendency toward better understanding. What unites all of these approaches is the recognition that the cosmic web, the large-scale structure of the universe, with its voids and filaments and clusters and walls, encodes the most comprehensive available record of cosmic history. It records the initial conditions set by inflation in the statistical properties of the density field. It records the physics of the early plasma and the baryon acoustic scale. It records the nature of dark matter in the clustering properties of halos and the internal dynamics of galaxies. It records the nature of dark energy in the growth rate of structure and the expansion history encoded in distances and redshifts. It records the properties of neutrinos in the small-scale matter power spectrum. It records the history of baryonic processes, star formation, feedback, chemical enrichment in the properties of galaxies as a function of their environment. The cosmic web is not just where matter is. It is the most complete record we have of everything that has happened in the universe since the first quantum fluctuations of inflation were frozen into the seeds of structure. Reading that record, with increasing precision and increasing comprehension, is the central enterprise of cosmology, and it will not be completed in any single lifetime or any single generation of instruments, or perhaps any single era of human civilization. There is a perspective worth holding here. We are not observers external to the system, we are part of it. The atoms in our bodies were forged in stars that lived and died before the sun was born. The carbon in organic molecules, the oxygen in every ocean on Earth, the iron in blood, all synthesized in stellar interiors and scattered into the interstellar medium by supernova explosions, collected into a molecular cloud, collapsed into the solar system, concentrated on a planet, and eventually assembled into the chemistry of biology. We are matter that has passed through stars, through the interstellar medium, through the chemistry of a young planet, and arrived at the condition of being able to study the structure from which it came. The void we inhabit is not a prison. It is a vantage point. From inside the KBC void, we look outward and see the walls of the surrounding structure, the filaments and sheets of galaxies that bound our emptiness at distances of hundreds of millions of light years, beyond them more voids, beyond those more filaments. The pattern repeats to the limit of our instruments, and presumably beyond. The universe is not the simple, smooth medium that the simplest models predicted. It is threaded, striated, bubbled, a structure of almost baroque intricacy built from the simplest possible initial conditions by the simplest possible forces, operating across the simplest possible laws. That simplicity at the base produces, over sufficient time and scale, something that looks anything but simple. The cosmic web, the voids, the walls, the anomalies at the edge of what theory can accommodate each of these is a statement about the universe we inhabit. Each of them tells us something about the initial conditions set by inflation, about the dark matter that shaped the gravitational skeleton, about the dark energy that is currently pulling the structure apart, about the ordinary matter that lights the threads of the web and allows us to trace the pattern. The web is not just a description of where galaxies are. It is the record of everything that has happened since the Big Bang, every fluctuation, every collapse, every merger, every explosion, every billion years of gravitational evolution imprinted in the positions and motions of billions of objects across billions of light years. And at the center of the largest of the known voids on a planet orbiting an unremarkable star in an unremarkable arm of a barred spiral galaxy that is itself orbiting within a supercluster of 10,000 galaxies that is itself flowing outward from a void into the filaments of the cosmic web. We continue to look armed with instruments of increasing sensitivity, models of increasing sophistication, simulations of increasing resolution, algorithms of increasing power, and questions that do not diminish as our knowledge grows. They multiply, they deepen, they clarify, and in clarifying reveal how much remains in the dark between the filaments, in the spaces between everything we can see. The Buddha's void was a shock because it was unexpectedly large. The KBC void is a challenge because we live inside it. The cold spot is a mystery because nothing in the standard model fully accounts for it. Webb's galaxies are a puzzle because they are more matured than they should be. The Hubble tension is a discrepancy that the best available physics cannot yet explain. The Hercules Corona Borealis Great Wall is a structure that, by the standards of the cosmological principle, should not exist. And yet all of these things are there, in the data, confirmed and reconfirmed by independent analyses using independent instruments. The universe does not especially care about our theoretical expectations. It is what it is. The history of cosmological thought is, in one reading, a history of expanding horizons, each generation of instruments revealing that the universe is larger, older, more structured, and more surprising than the previous generation could have imagined. Galileo's telescope revealed the moons of Jupiter and the phases of Venus, demolishing the Ptolemaic cosmology that had placed Earth at the center of a small, ordered universe. Herschel's systematic surveys of the night sky revealed the Milky Way as a disc-shaped system of stars and hinted at the existence of what he called island universes beyond it. The spectroscopic work of the 19th century revealed that stars are made of the same elements as the Sun and that the recession velocities of the nebulae, later identified as galaxies, implied a universe in motion. Hubble's observations in the 1920s established that the universe is expanding and that the galaxies are its fundamental units, each one a system of billions of stars separated from its neighbors by millions of light years. The discovery of the cosmic microwave background in 1965 by Penzias and Wilson, a serendipitous detection of the afterglow of the Big Bang while testing a new radio antenna for Bell Telephone Laboratories, confirmed the hot Big Bang model and established the temperature and isotropy of the early universe. The COPE satellite, launched in 1989, discovered the tiny temperature fluctuations in that background, the seeds of all cosmic structure, just as inflation predicted, earning John Mather and George Smoot the Nobel Prize in 2006. Each of these discoveries shifted the center of the universe away from wherever previous imagination had placed it. The Earth is not the center, the Sun is not the center, the Milky Way is not the center. Even the observable universe, the sphere of causally accessible space-time centered on our position, is not special in any cosmological sense. Any other observer anywhere else in the universe would have an equally valid center of their own observable sphere and would perceive the same large-scale structure in the same statistical sense, even if the specific galaxies and voids they observed were different. The cosmological principle, the foundation of modern cosmology, encodes this understanding. The universe has no center and no edge, only the local horizon that each observer imposes on their own experience. This is perhaps the most philosophically radical conclusion that cosmology has reached, not merely that the universe is large, but that there is no privileged vantage point within it. Every observer is simultaneously at the center of their own observable universe and in no special position relative to the whole. The void in which the Milky Way is embedded, the KBC void, 2 billion light-years in diameter, is large by any human measure. But it is finite and it is bounded. It has walls. Those walls contain galaxies. Beyond the walls, more voids. The pattern of voids and filaments and clusters continues in all directions to the horizon of the observable universe. And beyond that horizon, in the unobservable regions that are in principle forever inaccessible to us. The pattern presumably continues as well, statistically similar, though locally different. The scale of this picture makes it difficult to convey in any medium. Numbers help. 46 billion light-years for the observable universe, 2 billion for the KBC void, 1 billion for the Eridanus supervoid, 10 billion for the Hercules Corona Borealis Great Wall, 14 billion for the age of the universe, 100 billion for the number of galaxies in the observable universe, 100 billion for the number of stars in a typical galaxy. These numbers can be arranged in order of magnitude, compared and contrasted, embedded in sentences, but the mind that can hold 1 light-year in anything like genuine comprehension, not as an abstraction, but as a felt distance, an intuited scale, is probably not a human mind. We work with symbols for quantities our intuitions cannot encompass, and we construct partial models that capture some aspects of the reality without capturing the reality itself. What we can hold, and what is perhaps more important than the numbers, is the pattern. The cosmic web, voids and filaments and clusters, the foam of the universe is a pattern that our instruments have revealed and our mathematics has explained. It is a pattern that makes predictions about where galaxies will be, about how matter will cluster, about how the expansion rate will evolve, about what the microwave background will look like at different angular scales. It is a pattern that has been checked against hundreds of independent observations and found to be correct, with the ongoing exceptions and tensions that mark the frontier between the known and the unknown. And it is a pattern that connects the smallest and the largest scales in the observable universe through a single coherent narrative. The quantum fluctuations of inflation became the temperature fluctuations of the microwave background. The temperature fluctuations became the seeds of the first density perturbations. The density perturbations grew under gravity, guided by the dark matter scaffolding into the first halos and galaxies. The galaxies assembled along filaments. The filaments surrounded voids. The voids grew the clusters at the nodes of the web accumulated mass. The universe built up its structure over billions of years, from quantum foam to cosmic foam, from uncertainty at the smallest scales to pattern at the largest. And in one particular galaxy, in one particular solar system, on one particular planet, matter arranged itself into the form of observers, beings capable of detecting photons, measuring redshifts, building telescopes, running simulations, and reconstructing. From inside the structure, the story of how the structure came to be, the void we inhabit is not nothing. It is the largest coherent under-death region in the observable universe, an anomaly by the standards of the cosmological model that describes it, a challenge and a clue and a home. It surrounds us in every direction, its walls hundreds of millions of light years away, its interior populated by a handful of isolated galaxies evolving quietly in the cosmic slow lane. We sit near its center, looking outward, and what we see when we look hard enough with the right instruments across the full electromagnetic spectrum and now also in gravitational waves is the web. The pattern that the universe has been weaving since inflation ended. The structure that dark matter and dark energy and gravity and quantum mechanics together produced from the simplest possible beginning. Every observational program underway today. DESI measuring 40 million galaxy redshifts, Euclid mapping 1 billion galaxy shapes, Webb peering into the first 500 million years of cosmic history. LIGO listening for gravitational waves from merging black holes. The square kilometer array mapping the neutral hydrogen of the epoch of reionization CMB-S4. Extracting every last signal from the cosmic microwave background is, at its deepest level, an effort to read this pattern more completely. To understand not just where the filaments are and where the voids are, but why they are the size they are. Why the voids are as empty as they are. Why the expansion rate measures differently in different ways. Why the first galaxies were more organized than the standard model expected, why the cold spot is colder than it should be, why we live inside the largest known underdensity in the observable universe. Some of these questions will be answered in the coming decades, others will require generations of effort and instruments not yet conceived. And some, the nature of dark matter, the nature of dark energy, the ultimate fate of the universe, the physics of inflation, may require conceptual revolutions comparable to those introduced by general relativity and quantum mechanics. Revolutions that will make the current framework look as incomplete as Newtonian mechanics looks in retrospect. The universe does not reveal itself completely to any single generation. Each generation sees further than the last and leaves for the next a horizon that has been pushed back but not eliminated. And between the filaments, in the dark interior of the bubbles, the voids wait growing slowly, draining slowly, sending their matter outward toward the denser structures at their boundaries. They are not empty. They are the space in which the next questions live. They are the negative space of the cosmic web, defined by absence, shaped by surroundings, growing with time, and they are, measured by volume, what the universe mostly is. And the longer we look into them, the more clearly we see that what we took for nothing is, in fact, where the hardest problems hide, where the universe keeps its silences, and where every silence examined with sufficient care and time, and the ingenuity of observers who refuse to stop looking, turns out to contain something we had not expected to find. Between the filaments, in the dark interior of the bubbles, the voids wait, growing slowly, draining slowly, sending their matter outward toward the denser structures at their boundaries. They are not empty. They are the space in which the next questions live. They are the inverse image of everything we have built and measured and mapped. The silence between the words of a sentence, whose full meaning we do not yet understand. And the longer we look into them, the more clearly we see that what we took for nothing is, in fact, where the hardest problems hide, where the universe keeps its silences, and where every silence examined with sufficient care and time and ingenuity turns out to contain something we had not expected to find.